There is a planet where ice burns at 4,000 degrees Fahrenheit, not melts, burns. Solid water, locked into a crystalline structure by pressures so extreme they rewrite the rules of chemistry, staying frozen while the surface temperature climbs high enough to vaporize lead. And it is not alone. Out there, in the catalogue of confirmed exoplanets, are worlds that should not be possible. A gas giant darker than coal, absorbing 99% of all light that touches it, blacker than anything we have ever manufactured on Earth. A planet where temperatures spike by more than 1,000 degrees in 6 hours, whipping through an orbit so violent it has turned the entire atmosphere into a hurricane that never stops. A rogue world, wandering between the stars, with no sun to orbit and no light to warm it, drifting alone through the void for 12 million years. These are not theoretical, they are not modeling errors, they are not marginal detections buried in noisy data. These planets have been confirmed, measured and catalogued, and every single one of them breaks something fundamental about what we thought we understood. For most of human history, planets meant one thing: rocky worlds close to the sun, gas giants farther out, moons in predictable orbits, systems that behaved. Then we built telescopes powerful enough to look beyond our solar system, and the universe showed us what it actually does when we are not looking. What we found out there is not a collection of familiar worlds with minor variations. It is a gallery of impossibilities, and the deeper we look, the stranger it gets. This is the story of 12 planets that should not exist, and what they reveal about a cosmos that has never cared what we think is reasonable. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Our journey will move from searing inner orbits to impossible storms, from stripped worlds to the aftermath of dying stars, and finally into the darkness between them. What emerges may change the scale of our cosmic imagination and deepen the mystery of why this world still endures amid such unforgiving possibilities. We thought we knew what a planet was. For most of human history, that seemed like the easy part. A planet was a world. It orbited a star. It followed predictable rules, stable orbits, and reasonable temperatures. Rocky ones stayed close to their suns. Gas giants lived farther out where the cold made sense. Moons orbited planets. Planets orbited stars. Everything had a place, and that place made sense because we lived in it. Then we looked outside our own neighborhood, and the universe laughed at us. The first confirmed exoplanets, planets orbiting stars other than our Sun, were discovered in 1992, not around a normal star, around a pulsar, a dead star. The shredded corpse of a supernova spinning hundreds of times per second, blasting radiation in every direction, and somehow, impossibly, there were planets orbiting it. Worlds that had either survived the death of their parent star or formed afterward from the wreckage. Neither option made sense. The discovery was so strange that for years some astronomers refused to believe it counted. Those aren't real planets, they said. They're anomalies, debris. Call them whatever you want, but don't call them planets. Except they were planets, and they were just the beginning. By 2009, NASA launched the Kepler Space Telescope with a single mission: find Earth-sized planets orbiting other stars. See if we're alone. Kepler stared at a small patch of sky containing about 150,000 stars and watched. For 4 years, it recorded every flicker, every dip in brightness, every time a planet passed in front of its star and cast a shadow. By the time Kepler's primary mission ended, it had identified thousands of planetary candidates, thousands, in one tiny corner of one galaxy. And what it found was not a universe filled with copies of Earth. It was a cosmic junkyard of worlds that by every rule we thought we understood should not exist. Hot Jupiters, gas giants the size of Jupiter, orbiting closer to their stars than Mercury orbits our Sun. Planets where the surface temperature exceeds 4,000 degrees Fahrenheit and the atmosphere is being actively stripped away by stellar wind. Worlds so close to their stars that one side is permanently day and the other permanently night, locked in tidal synchronization the way our moon is locked to Earth. These planets take 3 days to complete an orbit, sometimes less. Our own Jupiter takes 12 years. The difference is not subtle. Ultra-short period planets. Rocky worlds, smaller than Earth, whipping around their stars in less than 24 hours. Places where a single year is shorter than a single day on Earth. Where the ground beneath your feet, if you could somehow stand on it, would be molten. Where the star overhead would fill half the sky and the heat would vaporize rock. Super-Earths. Planets larger than Earth, but smaller than Neptune, sitting in a size category that does not exist anywhere in our solar system. Rocky, maybe. Gassy, possibly. We don't actually know, because we've never seen one up close, and our models can't agree on what they should look like. The universe built an entire class of planet that our own star system skipped entirely, and nobody can tell you why. Rogue planets, worlds that don't orbit anything. They were ejected from their birth systems, flung into interstellar space by gravitational chaos, and now they drift alone through the void. No star, no warmth, no light, just endless cold and darkness for the rest of time. Some estimates suggest there could be billions of them wandering the Milky Way, more rogue planets than stars. An entire population of orphaned worlds nobody predicted and nobody knows how to count. Planets orbiting binary stars. 2 suns in the sky, like something out of science fiction, except it's not fiction. It's Kepler 16b, it's Kepler 47. It's an entire category of systems where the dynamics are so complicated that for decades astronomers assumed stable planetary orbits would be impossible. The gravity wells overlap, the orbits wobble, the radiation environment shifts depending on where both stars are in their dance. And yet there they are, planets, holding steady in configurations that shouldn't work. Planets orbiting dead stars, not just pulsars, white dwarfs. The cooling embers of stars that used to be like our Sun, now collapsed into objects the size of Earth, but with the mass of a sun. When a star dies and sheds its outer layers, the planetary system around it is supposed to be destroyed. Planets get swallowed during the red giant phase or flung out into space when the star loses mass. The ones that remain should be scorched, irradiated husks orbiting a stellar graveyard. And some of them are, but some aren't. Some are still there, quietly orbiting, as if nothing unusual happened at all. Every single one of these categories represents a direct contradiction of the model we built to explain how planets form. That model was elegant, simple, based entirely on the one planetary system we had ever seen, ours. In the classical picture, a star forms from a collapsing cloud of gas and dust. As the cloud spins, it flattens into a disk. The material in that disk gradually clumps together, building bigger and bigger objects. Close to the star, where it's hot, only rocky material survives. Farther out, beyond something called the frost line, water ice and other volatiles can condense. That's where the gas giants form. They get big enough to start pulling in hydrogen and helium from the surrounding disk, and they grow into massive worlds like Jupiter and Saturn. The small rocky worlds stay close. The big gassy ones stay far. The system stabilizes. Everything settles into predictable orbits. Done. That story worked beautifully for our solar system. Mercury, Venus, Earth, Mars, rocky, close to the Sun. Jupiter, Saturn, Uranus, Neptune, gassy, far from the Sun. Perfect fit. Textbook stuff. Every planetarium in the world had a model of it hanging from the ceiling. Every classroom taught it. It was the story of how planets worked. And then we looked at other systems and the story fell apart. Hot Jupiters should not exist. A gas giant cannot form close to its star. It's too hot. Water ice can't condense. Rocky grains can't stick together fast enough. There isn't enough solid material in the inner disk to build a core massive enough to capture gas. The physics doesn't work. And yet there they are, dozens of them, hundreds, giant planets orbiting closer to their stars than we ever thought possible. The explanation astronomers eventually settled on is called planetary migration. The gas giant forms farther out where the conditions allow it. Then something, interactions with the protoplanetary disk, gravitational nudges from other planets. Something pushes it inward. It spirals toward the star, plowing through the inner system, possibly destroying or ejecting smaller worlds along the way, until it finally settles into a scorching close orbit. The process is violent, chaotic, and nothing like the orderly assembly we imagined. Migration was not part of the original model. It was added later to explain the observations that didn't fit. And once you allow migration, once you admit that planets don't have to stay where they formed, the predictability vanishes. A planetary system stops being a static arrangement and becomes a dynamic battlefield where worlds can be shoved around, ejected, or consumed, depending on the outcome of gravitational interactions that play out over millions of years. That shift, that realization that planetary systems are not stable clockwork, but messy evolving environments, that was the first crack. The universe was telling us that the rules we wrote based on one example were incomplete. But we didn't know how incomplete until Kepler kept finding more and more systems that didn't look anything like ours. Super-Earths are the perfect example. They're everywhere. Kepler found them orbiting roughly 30 to 40% of the Sun-like stars it studied. They're one of the most common types of planets in the galaxy, and our solar system doesn't have one, not a single example. We skipped an entire planetary class that the rest of the galaxy seems to build routinely. Why? Nobody knows. The models that explain super-Earth formation work just fine in theory, but something about our system's formation, maybe Jupiter's early migration, maybe the timing of when the protoplanetary disk dispersed, prevented one from forming here. Or maybe we had one and it got ejected. Or maybe it's still out there, undiscovered, in the outer reaches of the solar system. That last possibility, by the way, is not science fiction. There's an active hypothesis called Planet 9, sometimes called Planet X, based on orbital anomalies in the Kuiper Belt. A group of researchers at Caltech announced evidence for it in January 2016. The idea is that there's a planet, something 5 to 10 times the mass of Earth, orbiting the Sun at an enormous distance, maybe 20 times farther out than Neptune. The gravitational influence of this unseen world could explain why certain icy objects in the outer solar system have weirdly clustered orbits. But here's the uncomfortable part. Nobody has seen it. No telescope has directly imaged it. It's a hypothesis supported by orbital mechanics, not observation. NASA's official position is that the existence of this distant world remains theoretical at this point. So even our own solar system, the one planetary system we've studied for centuries, the one we thought we understood completely, might still be hiding a planet. That should tell you something about how much we don't know. The unsettling thing about exoplanets is not that they're rare, it's that they're common. Studies suggest at least 1 in 10 stars hosts an Earth-sized planet in a temperate orbit. Some analyses put the number closer to 1 in 3. There are an estimated 100 to 400 billion stars in the Milky Way. Do the math. There could be tens of billions of Earth-sized worlds in our galaxy alone. And if even a small fraction of those worlds are as strange as the ones we've already found, the galaxy is filled with places that defy every intuition we've developed about what a planet should be. The diversity is the problem. If hot Jupiters were the only oddity, we could write them off as a quirk of certain types of systems. If super-Earths were the only mystery, we could focus our models on explaining them. But it's not one category, it's all of them. Every new discovery adds another planet that shouldn't exist according to the models built from the previous discoveries. The universe is not following a script. It's improvising, and the results are stranger than anything we imagined when we thought 9 planets orbiting one star in tidy concentric circles was the template. And we haven't even started talking about the truly disturbing ones yet. The planets that don't just violate our models, but seem to violate basic physics. Worlds where ice burns, worlds darker than coal, worlds being actively devoured by their stars, trailing comet-like tails of vaporized atmosphere behind them as they spiral toward destruction. Those planets exist. They're not hypothetical, they're out there right now, orbiting real stars, and we've measured them, photographed them, analyzed their atmospheres. They're as real as Earth, and they make no sense. The question isn't whether these planets exist. The data is clear. The question is why. Why does the universe build worlds like this? What processes allow a planet to form in a place where theory says it should be impossible? What are we missing in our understanding of gravity, chemistry, stellar evolution, or time that would make these aberrations fit into a framework that actually predicts them, instead of just reacting to them after the fact? There's a word astronomers use when an observation contradicts theory. They call it attention. It's a polite term. What it really means is that something is wrong. Either the observation is mistaken, which becomes harder to argue after you've confirmed it with multiple instruments, or the theory is incomplete. And if the theory is incomplete, then every conclusion drawn from that theory is suspect. Every prediction about where to look for habitable worlds, every assumption about how common Earth-like planets are, every estimate of how many civilizations might exist in the galaxy, all of it rests on models that are currently being rewritten because the planets we're finding don't match the planets we expected. The exoplanets we've discovered so far represent a tiny sample. Kepler stared at 0.25% of the sky. Most of the planets it found are big, because big planets are easier to detect. They block more light when they transit their stars. They tug harder on their stars, making the wobble easier to measure. The small rocky worlds, the ones that might actually resemble Earth, are harder to spot. We've found some, but the bias in our data is enormous. We're not seeing a representative sample of what's out there. We're seeing the loudest, brightest, most obvious examples. The fact that even this biased sample is full of impossible planets suggests that when we finally develop the tools to see the quieter worlds, the smaller ones, the ones in wider orbits, the strangeness is only going to deepen. Imagine you're an alien astronomer living on a planet orbiting a star 500 light-years from here. You point your telescope at our solar system and try to detect planets. What do you see? If you're using the transit method, you see nothing, because none of our planets cross in front of the Sun from your vantage point. If you're using the radial velocity method, measuring the wobble our planets cause in the Sun's motion, you might pick up Jupiter after watching for a decade or more. Maybe Saturn. You almost certainly miss Earth. It's too small. Its gravitational tug on the Sun is too weak. From your perspective, our solar system looks almost empty, a star with maybe 1 or 2 distant gas giants. You'd have no idea there are 4 rocky planets closer in. You'd never detect the asteroid belt. The Kuiper belt would be invisible. You'd look at our system and conclude that it's unremarkable. Quiet. Probably not worth a follow-up observation. We're doing the same thing in reverse. Every exoplanet catalogue we've assembled is filtered through the limitations of our instruments. The planets we've found are the ones we're capable of finding, not the ones that are actually there. And even with that narrow view, we're already drowning in worlds that break the rules. So what comes next? What happens when the James Webb Space Telescope, which can analyze the atmospheres of exoplanets in unprecedented detail, starts finding chemical signatures that don't fit? What happens when the next generation of ground-based telescopes, the ones with mirrors 30 meters across, come online and start directly imaging planets in systems we've only studied indirectly? What happens when we find something worse than a hot Jupiter or a rogue planet? What happens when we find a planet that's not just unlikely, but genuinely impossible? That's the journey this is going to take. We're going to look at the planets that shouldn't exist and ask very carefully what they mean, not just for planetary science, but for everything downstream of it. Because if planets can form in places we thought were sterile, if they can survive conditions we thought were lethal, if the universe builds worlds on a whim without consulting our textbooks, then the map we've drawn of where life might arise, that map is wrong too. And if the map is wrong, then we've been looking in the wrong places. The unsettling familiarity of these worlds is that they orbit stars just like ours. They formed from the same basic ingredients: hydrogen, helium, dust, the leftovers of dead stars. They follow the same physical laws. Gravity works the same way everywhere. Chemistry doesn't change depending on your galactic zip code. The rules are universal, and yet the outcomes are wildly different, which means the rules, as we've written them, are missing something big. That realization is the foundation we're standing on as we move deeper into this. The universe doesn't care what we think is possible. It builds what it wants, and our job, the only job we've ever had, is to look at what it built and try to figure out why. Most of the time, that process is slow, careful and boring. Data collection, model refinement, incremental progress. But every so often, we find something that doesn't fit, and the whole structure shakes. These 12 planets, the ones we're about to walk through, are not incremental. They're not minor adjustments to the model, they're earthquakes. And the fact that we're still arguing about how they exist tells you everything you need to know about how far we still have to go. The first stop on this list is heat. Not the comfortable warmth of a sun-kissed afternoon, but heat that melts iron, vaporizes rock, and tears atmospheres apart molecule by molecule. We're going to places where stars have stopped being life-givers and turned into executioners. We need to talk about heat, not the kind you feel stepping out of an air-conditioned building into summer sunlight. Not the kind that makes asphalt shimmer or turns car interiors into ovens. We're talking about heat that operates on a scale so far beyond human experience that the words we use to describe it stop meaning anything useful. Heat that doesn't warm, it destroys. There's a category of planets astronomers call hot Jupiters, and the name is almost offensively inadequate. Jupiter, our Jupiter, orbits the Sun at a distance of about 778 million kilometers. It takes nearly 12 Earth years to complete one trip around. The temperature at the top of its cloud layers hovers around -145 degrees Celsius. Cold enough to freeze carbon dioxide solid. Cold enough that if you could somehow stand on a platform above those clouds, your breath would turn to ice crystals before it left your mouth. Jupiter is cold, distant and stable. A gas giant in the place gas giants are supposed to be. Hot Jupiters are not that. They're gas giants orbiting closer to their stars than Mercury orbits our Sun. Some complete an orbit in less than 3 days. The temperature at their cloud tops isn't -145 Celsius, it's thousands of degrees. The distinction between a hot Jupiter and Jupiter is not a matter of degree, it's a matter of category. They share a name because they're both large and mostly made of hydrogen and helium. Beyond that, they have almost nothing in common. And the first question anyone asks when they hear about these planets is obvious. How? How does a gas giant end up that close to its star? The answer involves something called planetary migration, a process we touched on earlier, but it's worth unpacking here because it's not just an interesting footnote. It's a violent, chaotic reshaping of an entire planetary system, and it explains why hot Jupiters exist at all. A gas giant cannot form close to its star. The inner regions of a protoplanetary disk, the swirling cloud of gas and dust surrounding a young star, are too hot. Water ice, which is one of the key building blocks for a planet's solid core, can't condense that close in. It evaporates. Without ice, you can't build a core massive enough to start pulling in hydrogen and helium from the surrounding gas. You need a solid foundation first, and that foundation only forms beyond the frost line, the distance from the star where temperatures drop low enough for ice to exist. So the gas giant forms farther out, where it's cold, where the conditions allow it. And then something happens. Maybe interactions with the protoplanetary disk itself cause the planet to lose orbital energy and spiral inward. Maybe gravitational interactions with other planets kick it into an unstable orbit that eventually decays. Maybe a close encounter with a passing star disrupts the system. The exact mechanism varies depending on the system, and astronomers are still arguing about which processes dominate. But the result is the same. The planet migrates inward, plowing through the inner system, possibly ejecting smaller rocky worlds or flinging them into the star. It settles into a tight orbit, and the star's radiation starts cooking it. That migration isn't gentle. It's not a slow, graceful drift. It's a wrecking ball moving through a planetary neighborhood that used to be stable. If Earth had formed in a system with a migrating hot Jupiter, we wouldn't be here. We'd have been scattered into interstellar space or vaporized. The fact that our solar system doesn't have a hot Jupiter is one of the reasons life had time to develop here. We got lucky. Most systems don't. Let's start with HD 80606b because it's a perfect example of what happens when orbital mechanics go wrong. This planet orbits a star in the constellation Ursa Major, about 190 light-years from Earth. It's a gas giant, roughly 4 times the mass of Jupiter, and at first glance it looks like a fairly standard hot Jupiter, except for one detail. Its orbit is absurdly eccentric. Most planets in our solar system orbit in near-perfect circles. Earth's orbit is so close to circular that the difference between its closest approach to the Sun and its farthest point is only about 5 million kilometers. For a planet traveling 150 million kilometers from the Sun on average, that's nothing, a rounding error. HD 80606b's orbit is nothing like that. Its orbit is stretched into a long, narrow ellipse. At its farthest point, it's about 133 million kilometers from its star. At its closest, it plunges to just 4.5 million kilometers. The difference is a factor of 30. Imagine living on a world where winter meant being far enough from your sun that water froze solid, and summer meant being close enough that the oceans boiled away. Except the seasons wouldn't take months, they'd take days. HD 80606b completes one orbit every 111 Earth days, and the swing from aphelion, the farthest point, to perihelion, the closest point, happens over the course of just a few days. The temperature doesn't rise gradually, it spikes. Observations of HD 80606b using infrared telescopes have tracked this process in real time. As the planet approaches its star, the dayside temperature climbs from around 500 degrees Celsius to more than 1,200 degrees Celsius in less than 6 hours. 6 hours. That's faster than most ovens can preheat. The atmosphere doesn't have time to adjust. The thermal energy dumping into the planet's dayside during perihelion passage is so intense that it drives supersonic winds racing around the planet, trying to redistribute the heat. The wind speeds are estimated at several kilometers per second. For reference, the fastest winds on Earth, inside the most violent tornadoes, reach maybe 130 meters per second. On HD 80606b, the wind is 20 times faster. The reason the temperature spike is so extreme involves more than just the star's radiation. Yes, being closer to the star means receiving more light, and that matters. But there's a second source of heat that's just as important: tidal heating. Tidal heating is what happens when a planet's shape gets squeezed and stretched by gravity. If you've ever bent a paperclip back and forth repeatedly, you've felt it get warm. That's the same basic process. Mechanical stress converts to heat. Now imagine the paperclip is an entire planet, and the force bending it is the gravity of a star pulling unevenly on the near side versus the far side. That's tidal heating. In a circular orbit, tidal heating is relatively small because the gravitational pull from the star stays constant. But in an eccentric orbit, like HD 80606b's, the tidal forces fluctuate wildly. When the planet is far from the star, the tidal stress is low. As it swings inward, the stress ramps up. The planet gets pulled into a slightly elongated shape. Then, as it swings back out, the stress drops and the planet rebounds. This squeezing and relaxing cycle happens every orbit, and every time it does, the planet's interior heats up. Europa, one of Jupiter's moons, is kept warm by the same process. Jupiter's gravity flexes Europa's interior, generating enough heat to maintain a liquid ocean beneath its icy shell despite being far from the Sun. HD 80606b is experiencing the same physics, but on a scale that makes Europa look like a rounding error. The tidal heating on HD 80606b during perihelion passage is thought to dump as much energy into the planet as the star's radiation does, maybe more. The planet is essentially being cooked from two directions at once: radiation from above, tidal friction from within. What does that do to a planet over time? The short answer is, we don't know yet, because we've only been observing HD 80606b for a couple of decades, and orbital evolution on this scale plays out over millions of years. But the long-term prognosis isn't good. Tidal interactions between a planet and its star tend to circularize orbits. The energy that goes into heating the planet has to come from somewhere, and it's being stolen from the planet's orbital motion. Over millions of years, HD 80606b's orbit should gradually become less eccentric, which would smooth out the temperature swings and reduce the tidal stress. Eventually, it might settle into a circular orbit close to its star and become a more typical hot Jupiter. But that process takes time. Right now, HD 80606b is caught in the middle of that transition, enduring temperature swings that would shred any atmosphere a rocky planet might have tried to hold on to. And HD 80606b, for all its extremes, is not even close to the worst example. That distinction belongs to Kelt 9b, a planet that operates on a level of heat so extreme that calling it hot is like calling the ocean damp. Kelt 9b orbits a star called HD 195689, an A-type star located about 670 light-years from Earth in the constellation Cygnus. A-type stars are bigger, brighter, and much hotter than our Sun. They burn through their fuel faster, live shorter lives, and emit far more ultraviolet radiation. HD 195,689 has a surface temperature of around 10,000 degrees Celsius. For comparison, the Sun's surface sits at about 5,500 degrees. The star Kelt 9b orbits is nearly twice as hot as ours, and Kelt 9b orbits that star at a distance of less than 7 million kilometers. It completes one orbit every 36 hours. 1.5 Earth days. The planet is tidally locked, meaning the same side always faces the star, the way the moon always shows the same face to Earth. The day side of Kelt 9b never experiences night. It is perpetually blasted by radiation from a star hot enough to make the sun look dim. The temperature on Kelt 9b's day side has been measured at around 4,300 degrees Celsius. Some estimates push it closer to 4,600 degrees. At those temperatures, molecules don't survive. Chemical bonds break apart. Water, if there were any, would decompose into hydrogen and oxygen atoms. Carbon dioxide splits into carbon and oxygen. Methane, ammonia, any of the compounds you might expect in a gas giant's atmosphere, they can't exist. What you're left with is an atmosphere of individual atoms stripped of their molecular identities, glowing with thermal radiation. Iron, which melts at 1,538 degrees Celsius and boils at 2,862 degrees Celsius, doesn't just melt on Kelt 9b, it evaporates. Titanium, with a boiling point of 3,287 degrees Celsius, is present in the atmosphere in gaseous form. Observations have detected atomic iron, atomic magnesium, and ionized calcium in the upper atmosphere of Kelt 9b, elements that should be locked away in the planet's core or condensed into solid grains, not floating around as free atoms. And here's the part that sounds like a mistake the first time you read it. Kelt 9b is hotter than the surface of many stars. Red dwarfs, the most common type of star in the galaxy, have surface temperatures around 2,500 to 4,000 degrees Celsius. Kelt 9b, a planet, is hotter than that. It's not just orbiting a star, it's approaching stellar temperatures itself. The only reason it qualifies as a planet at all is that it doesn't generate its own energy through fusion. It's being heated externally, but from an observational standpoint, the distinction is getting harder to draw. The atmosphere of Kelt 9b is not stable. It can't be. The planet is losing mass. The intense ultraviolet radiation from its host star is stripping away the outer layers of the atmosphere faster than the planet's gravity can hold them down. Hydrogen, the lightest and most abundant element, is escaping into space in a constant stream. Astronomers have detected an extended envelope of hydrogen around Kelt 9b, a cloud of gas being ripped away by the stellar wind and blown off into space. The planet is evaporating. This process, called atmospheric escape, is not unique to Kelt 9b. Many hot Jupiters experience it to some degree, but Kelt 9b is losing atmosphere at a rate that's extreme even by hot Jupiter standards. Current estimates suggest it's shedding somewhere between 10 to 100 million kilograms of material per second. Over the course of a year, that adds up to trillions of kilograms. Over millions of years, that becomes a noticeable fraction of the planet's total mass. Kelt 9b is not going to survive indefinitely. It's being consumed by its star. Not swallowed whole, not yet, but slowly eroded, atom by atom, until eventually there won't be enough mass left to call it a planet. What remains might be a dense core, a remnant of whatever solid material existed beneath the hydrogen and helium envelope. Or it might be nothing. The planet could be completely disintegrated, scattered into the stellar wind, leaving behind only a faint trace of elements in the star's spectrum as evidence that something used to be there. This is the fate of planets that orbit too close to their stars. They don't get to exist on comfortable timescales. They're temporary, geological accidents waiting to be undone by the same processes that created them. The detection of molecules in exoplanet atmospheres is one of the major goals of modern astronomy. When the James Webb Space Telescope analyzes the light passing through an exoplanet's atmosphere during a transit, it's looking for the chemical fingerprints of water vapor, carbon dioxide, methane, molecules that might indicate habitability or even biological activity. Kelt 9b represents the opposite end of that spectrum. It's a planet where chemistry, in the sense we normally think of it, has ceased to function. There are no molecules. There are only atoms, and those atoms are being stripped away before they have a chance to recombine into anything stable. And the strangest part of this, the part that keeps showing up in the data, is that these planets are not rare. Hot Jupiters as a class make up a significant fraction of the exoplanets discovered so far. Kelt 9b is an extreme example, yes, but it sits at one end of a continuous distribution. There are dozens of planets nearly as hot, hundreds that are hot enough to disintegrate molecules, thousands that orbit close enough to their stars that atmospheric loss is a major factor in their evolution. The universe is full of worlds being slowly consumed by their stars, and we only started noticing them a couple of decades ago. There's a term in planetary science called the Roche limit. It's the distance from a massive object, like a star or a planet, where tidal forces become strong enough to tear apart a smaller object held together only by its own gravity. Get closer than the Roche limit, and the difference in gravitational pull between the near side and the far side of the smaller object exceeds the object's ability to hold itself together. It disintegrates. Rings form from the debris. Moons get shredded. Planets, if they're unlucky enough to drift that close, get destroyed. Kelt 9b is not inside its star's Roche limit. Not yet, but it's close enough that the long-term outcome isn't in doubt. The tidal forces acting on it, combined with the atmospheric stripping driven by stellar radiation, are slowly pulling the planet apart. The timescale is measured in millions of years, maybe tens of millions, but on astronomical timescales that's a blink. Kelt 9b is doomed, and we're watching it die in slow motion. HD 80606b might have a different fate. Its eccentric orbit could eventually circularize, stabilizing the planet into a more sustainable configuration. Or it could spiral inward and end up like Kelt 9b, locked in a death grip with its star. The math depends on variables we can't measure precisely yet. The planet's internal structure, the efficiency of tidal dissipation, the exact history of how it migrated inward in the first place. Small changes in any of those factors alter the outcome. What both planets teach us is that proximity to a star is not a benign condition, it's a sentence. Stars are not passive light sources. They're active, radiating, magnetically complex objects that strip atmospheres, distort orbits, and generate tidal forces capable of reshaping entire worlds. And the closer you get, the more violent those interactions become. The planets we've looked at so far are defined by heat. Temperature is the variable driving every other process. The atmospheric chemistry, the wind patterns, the rate of mass loss, all of it flows from the fact that these worlds are being cooked by their stars. But heat is not the only way a star can make a planet uninhabitable. There are other mechanisms, quieter, stranger, that produce outcomes just as extreme. And the next planet we're going to visit doesn't glow with heat. It does the opposite. It absorbs light so completely that astronomers, when they first confirmed its existence, had trouble believing the data. A planet darker than charcoal, darker than coal, a world that swallows light and gives almost nothing back. We left off watching planets burn, worlds locked in death spirals around their stars, atmospheres peeling away atom by atom, surfaces glowing hot enough to vaporize iron, heat turned up so high that chemistry itself stops working the way it's supposed to. Those planets are bright, painfully bright. Point a telescope at Kelt 9b, and the thermal radiation alone is enough to make it visible across hundreds of light years. It glows like an ember. You could see it with instruments tuned to infrared, even if its star weren't there. Now we need to talk about the opposite problem. A planet so dark that when astronomers first measured its reflectivity, they assumed something had gone wrong with their instruments. A world that doesn't glow, doesn't shine, doesn't reflect. A planet that swallows light and refuses to give it back. The darkest known object orbiting any star in the galaxy, darker than charcoal, darker than coal, darker than the blackest paint human chemists have ever synthesized. Its name is TRES 2b, and it should not look like this. The discovery came in 2006, which in the timeline of exoplanet research feels like ancient history now, but at the time it was cutting edge. The Transatlantic Exoplanet Survey, TRES for short, was one of several ground-based networks scanning the sky for planets using the transit method. The process is straightforward in theory. Point a telescope at a star and watch. If a planet crosses in front of the star from our perspective, the star's brightness dips slightly. The amount of the dip tells you how big the planet is. The timing tells you how long the orbit takes. String together enough transits and you can map the entire system without ever directly imaging the planet itself. TRES 2b showed up as a periodic dip in the brightness of a star called GSC 3549 to 2811, later renamed TRES 2a for clarity. The star sits about 750 light-years away in the constellation Draco. Not particularly close, not particularly far. A perfectly ordinary sun-like star doing perfectly ordinary star things. The planet blocking its light turned out to be a gas giant, roughly 1.5 times the mass of Jupiter, slightly larger in radius, orbiting at a distance of just under 0.036 astronomical units. That puts it about 30 times closer to its star than Earth is to the Sun. Mercury, for reference, orbits at 0.39 astronomical units. TRES 2b is hugging its star so tightly that it completes one full orbit every 2.5 Earth days. So far, nothing unusual. By 2006, astronomers had already found dozens of hot Jupiters. TRES 2b looked like another entry in a growing catalogue. Big planet, close orbit, high temperature. Check, check, check. The discovery paper noted the basics and moved on. The planet's peculiarity wouldn't become apparent until 5 years later, when a team of researchers decided to measure something most people assumed would be routine. It's albedo. Albedo is the fraction of light a planet reflects. It's a number between 0 and 1. 0 means the object absorbs all incoming light and reflects nothing. 1 means it reflects everything and absorbs nothing. Fresh snow has an albedo around 0.8 to 0.9. Earth, with its mix of oceans, clouds and land masses, averages about 0.3. Jupiter sits around 0.5, mostly thanks to its thick clouds of ammonia ice crystals that bounce sunlight back into space. Even the moon, which looks bright in our night sky, only reflects about 12% of the light hitting it. Its albedo is 0.12. Darker than you'd think for something we associate with brightness, but still well within the range of normal rocky bodies. In 2011, David Kipping and David Spiegel published a study analyzing light curves from TRES-2b's transits and occultations. An occultation is when the planet passes behind the star from our perspective, disappearing from view. By measuring how much the total light from the system drops when the planet vanishes, you can figure out how much light the planet itself was contributing. Not light it generates, because planets don't make their own light, but light it reflects from its star. The difference between the transit depth, when the planet blocks the star, and the occultation depth, when the planet hides behind the star, gives you the albedo. The number they got back was 0.04, maybe as low as 0.01, depending on which model fit they used. The best estimate hovered around 0.04, meaning TRES-2b reflects roughly 4% of the light that hits it. Some later analyses pushed that number even lower. The planet absorbs at least 96% of incoming starlight, possibly as much as 99%. One paper described it as absorbing 99.9%, which, if true, would make it one of the most efficient light absorbers ever measured on any object anywhere. To put that in perspective, charcoal has an albedo of about 0.04. Coal sits around 0.05. Black acrylic paint, the kind you'd use to cover a wall if you wanted the darkest possible surface, reflects about 5 to 10% of visible light. TRES-2b is darker than all of them. Princeton University, covering the 2011 study, called it the most light-thirsty object in the known universe. NASA's exoplanet catalog describes it as the darkest planet ever discovered orbiting a star. Not the darkest gas giant, not the darkest hot Jupiter, the darkest planet. Full stop. Less reflective than coal. That statement sits in the scientific literature now as an established fact, and it's worth pausing on because it doesn't make sense. Gas giants are not supposed to be dark. Jupiter reflects half the light that hits it. Saturn reflects even more. Uranus and Neptune, despite being farther from the Sun and colder, still manage albedos above 0.4. They're blue-green and pale in visible light because their atmospheres are full of methane ice, water ice, ammonia, compounds that scatter light efficiently. Even hot Jupiters, planets roasted by their stars to temperatures well over 1,000 degrees, generally show albedos in the range of 0.1 to 0.3. They're darker than Jupiter, yes, because the heat prevents the formation of bright reflective clouds, but they're not black. TRES-2b is black, actually black. If you could somehow see it up close, floating in space with its star behind it, it would look like a hole, a sphere-shaped absence where light goes in and doesn't come out. The only reason you'd know it was there at all is the faint red glow from its own thermal radiation. The planet's dayside temperature is estimated at over 1,000 degrees Celsius, around 1,800 Fahrenheit. Hot enough that it emits a dim red light, the way a heating element on an electric stove glows when it's warming up. But that glow is faint. If you were looking at TRES-2b from a distance, the overwhelming impression would not be red. It would be darkness, deep, lightless, unsettling darkness. The natural question is why? What is happening in TRES-2b's atmosphere that allows it to absorb light this efficiently? And the uncomfortable answer is that no one is entirely sure. There are theories, good ones, theories backed by atmospheric models and chemistry and observations of other hot Jupiters, but none of them fully close the gap. None of them predict a planet this dark. The models get you partway there, and then they stop, and what's left is a remainder no one knows how to explain. The leading explanation starts with clouds, or rather, the lack of them. Jupiter's bright albedo comes almost entirely from its upper atmosphere, where temperatures are cold enough for chemicals like ammonia to condense into ice crystals. Those crystals form clouds, and those clouds reflect sunlight. It's the same reason Earth's clouds are white. Water droplets and ice particles scatter light in all directions. Some of that light bounces back into space. The more clouds you have, the higher your albedo. Hot Jupiters don't have cold upper atmospheres. The intense radiation from their nearby stars keeps the upper layers too warm for ammonia or water to condense. The chemicals that would normally form reflective clouds stay in gaseous form, and gases are much less efficient at scattering light than solid particles. The result is a darker planet. This explanation works well for moderately hot Jupiters. It explains why their albedos drop into the 0.1 to 0.3 range. But it doesn't explain TRES 2b. Even without clouds, an atmosphere full of hydrogen and helium should still scatter some light. Rayleigh scattering, the same process that makes Earth's sky blue, works on any atmosphere with gas molecules. TRES 2b's atmosphere should scatter at least a little light back toward space, but it doesn't. Or if it does, the amount is so small that it's swamped by whatever else is happening. The second part of the explanation involves chemistry, specifically chemicals that absorb light rather than reflect it. Sodium and potassium are two candidates. Both are common in gas giant atmospheres, and both are excellent at absorbing visible light when they're in atomic form. Observations of other hot Jupiters have detected sodium and potassium absorption lines in their spectra, meaning the light from the star passes through the planet's atmosphere and certain wavelengths get absorbed by these atoms before reaching our telescopes. If TRES 2b's atmosphere has a lot of sodium or potassium, and if those atoms are distributed throughout the upper atmosphere rather than confined to deeper layers, they could be soaking up a significant fraction of the incoming starlight. But sodium and potassium alone aren't enough. You need something more, something that absorbs across a broader range of wavelengths. That's where titanium oxide and vanadium oxide come in. These are metal oxides, compounds formed when metals like titanium or vanadium bond with oxygen. They're present in the atmospheres of the hottest gas giants, and they have a very useful, or in this case very problematic, property. They absorb strongly across the visible and near-infrared spectrum. Not just one color, all of them. A planet with enough titanium oxide or vanadium oxide in its upper atmosphere would appear dark because most of the light hitting it would be absorbed by these compounds before it had a chance to scatter. This model has some support. Studies of other hot Jupiters have found evidence for titanium oxide in their atmospheres, particularly in planets with temperatures above 1,500 degrees Celsius. TRES 2b, at over 1,800 degrees Fahrenheit, sits comfortably in that range. The heat would keep titanium and vanadium in gaseous form, allowing them to mix into the upper atmosphere. Add in sodium and potassium, and you've got a cocktail of light-absorbing chemicals that could plausibly push the albedo down into the range TRES 2b occupies. But, and this is the part that keeps researchers from calling the case closed, the chemistry only gets you so far. Even with titanium oxide, vanadium oxide, sodium and potassium all present in large amounts, atmospheric models struggle to reproduce an albedo as low as 0.04. They get close. They get to maybe 0.06 or 0.08. But squeezing out that last bit of reflectivity, driving the albedo down to coal-black levels, requires something extra, something the models aren't capturing. One possibility involves the planet's thermal structure. TRES 2b is likely tidally locked, meaning the same hemisphere always faces its star. The day side is in permanent noon, the night side is in permanent midnight. This creates extreme temperature gradients. The day side could be hundreds of degrees hotter than the night side, and that temperature difference drives winds, fast winds, supersonic winds possibly, racing from the hot side to the cold side and back again in massive circulation patterns that wrap around the entire planet. Those winds could be redistributing chemicals in ways that enhance light absorption. Maybe titanium oxide condenses into tiny particles on the night side where it's cooler. Then those particles get carried back to the day side by the wind, where they re-evaporate and spread throughout the upper atmosphere. The result would be a day-side atmosphere loaded with light-absorbing material, constantly replenished by circulation from the night side. That kind of dynamic process is hard to model because it depends on the details of atmospheric circulation, which in turn depend on the planet's rotation rate, its internal heat, the efficiency of heat transport, all variables we can't measure directly from 750 light-years away. Or maybe there's something else entirely. Some chemical we haven't thought of, some reaction we don't understand, some process unique to the specific conditions inside TRES-2b's atmosphere that we won't figure out until we can study the planet in much finer detail than current instruments allow. The frustrating part is that TRES-2b isn't hiding. It's right there. We know where it is. We've watched it transit its star dozens of times. We've measured its mass, its radius, its orbital period, its temperature. We have data. And the data tells us the planet is absurdly dark, and we still can't build a model that fully explains why. There's something deeply unsettling about an object that absorbs light this efficiently. Light is how we see. It's how we gather information about the universe. Point a telescope at something, and the light reflected or emitted by that object carries information back to you. Its color tells you its temperature. Its spectrum tells you its composition, its brightness tells you its size and distance. That entire framework depends on light making the return trip. When you point a telescope at TRES-2b, most of the light doesn't come back. The planet swallows it. What little thermal glow it emits is overwhelmed by the brightness of its star, making the planet almost invisible except during transits and occultations when its position is revealed by the shadow it casts or the shadow cast on it. If you were standing on a spacecraft near TRES-2b, the experience would be profoundly wrong. The star, TRES-2a, would dominate the sky. A blazing white disk, 30 times larger than the Sun appears from Earth. It would flood the scene with light, illuminating everything around you. Your spacecraft, your instruments, the inside of your cabin if you had a window. Everything would be drenched in starlight. And floating in front of you, close enough to resolve as a disk, would be TRES-2b, a massive planet 1.5 times the size of Jupiter, physically large enough to cover a noticeable chunk of your field of view. And it would be black, not shadowed. Not dark gray, black, a perfect circle of nothingness, slightly tinged with red if you looked carefully, cutting a hole in the star-filled background. The cognitive dissonance would be overwhelming. Your brain knows planets reflect light. That's what planets do. You've seen Jupiter. You've seen Saturn. They're bright. They catch the sun and throw it back. TRES-2b would do the opposite. It would sit there, soaking up the light, and all your instincts would scream that something was wrong. The philosophical question lurking underneath all of this is what it means for a planet to be that dark. We associate darkness with the absence of energy, with cold, with death. But TRES-2b isn't cold, it's scorching. Its atmosphere is hot enough to vaporize metals. The darkness isn't a lack of energy, it's a consequence of energy being trapped. The light goes in, gets absorbed, converts to heat, and that heat stays in the atmosphere, warming it further, which changes the chemistry, which makes the atmosphere absorb even more light. It's a feedback loop, a runaway process where the planet's darkness reinforces itself. And here's the part that connects to a broader point. TRES-2b is not unique in kind, it's unique in degree, There are other hot Jupiters with low albedos, other planets darker than Jupiter. TRES 2b just happens to be the darkest one we've found so far. That phrasing is important, so far. Implies there could be others, implies we might find planets even darker. And if we do, if there's a whole class of ultra-dark planets out there, it changes the way we think about what gas giants look like. For decades, our mental image of a gas giant was based on Jupiter and Saturn, banded, colorful, bright. When science fiction artists drew exoplanets, they drew variations on that theme. Different colors, maybe, different band patterns, but always some level of brightness, always something you could see. TRES 2b forces a revision. Gas giants can be black. They can be so dark that even from close range they're hard to see. And if that's true, then our surveys of exoplanets, which rely heavily on detecting the light planets reflect or block, are missing some. The darkest ones are slipping past us. We see them when they transit their stars because the shadow is obvious. But in direct imaging surveys, where you're trying to photograph a planet by the light it reflects, a planet like TRES 2b would be almost invisible. You'd look right at it and see nothing. That has implications for how we count planets, how we estimate how many gas giants are in the galaxy, how we build statistical models of planetary systems. If a significant fraction of hot Jupiters are much darker than we expected, then the fraction we've detected is smaller than we thought, which means the total population is larger, which means our understanding of how common these planets are, and by extension how planetary migration works, is based on incomplete data. The universe might be full of dark planets we haven't noticed yet because they're too good at hiding. TRES 2b also raises uncomfortable questions about habitability. Not for itself, obviously. A gas giant with no solid surface and a temperature over 1,800 degrees Fahrenheit is not hosting life as we understand it. But imagine a smaller planet, rocky, orbiting in a habitable zone, with an atmosphere that for whatever reason absorbs light as efficiently as TRES 2b does. What happens to that planet? Does it heat up? Does the absorbed light warm the surface and atmosphere until the planet enters a runaway greenhouse state like Venus? Or does the energy get radiated away as thermal radiation quickly enough to maintain balance? The answer depends on atmospheric composition, greenhouse gas concentrations, the planet's distance from its star. But the starting point, a surface that reflects almost nothing, tilts the energy balance in a dangerous direction. Less reflected light means more absorbed energy. More absorbed energy means higher temperatures. Higher temperatures can trigger feedback loops that make the planet hotter still. Earth reflects about 30% of the sunlight that hits it. That reflection is part of what keeps us cool enough for liquid water. If Earth's albedo dropped to 0.04, if our atmosphere and surface suddenly started absorbing 96% of incoming sunlight instead of 70%, the planet would cook. Not instantly, not in a matter of days, but over time, the extra energy would accumulate. Temperatures would rise, ice would melt, oceans would evaporate. Water vapor, a greenhouse gas, would trap even more heat, driving temperatures higher still. The end state would look a lot like Venus, hot, dry, hostile to anything resembling life. TRES 2b is not a preview of Earth's future. Our atmosphere is nothing like TRES 2b's, and we're not in danger of turning into a hot Jupiter. But TRES 2b is a preview of what's possible. It's proof that planets can enter states we didn't predict. States where the normal rules, the ones that say gas giants should be bright, the ones that say planets in a given temperature range should have certain types of clouds, those rules stop applying. And if the rules stop applying for gas giants, they can stop applying for rocky planets too. There's no law of physics that prevents a rocky world from developing a dark surface or a light-absorbing atmosphere. We haven't found one yet. That doesn't mean they don't exist. The study of TRES 2b continues. The James Webb Space Telescope has the sensitivity to analyze its atmosphere in far greater detail than was possible with earlier instruments. Webb can take spectra during transits and occultations, picking apart the chemical composition layer by layer. If titanium oxide is there, Webb will see it. If there's something else, some exotic compound no one predicted, Webb has a chance of identifying that too. The data will take time to collect and analyze. TRES 2b's host star is not particularly bright, and the planet's signal is faint. But eventually, someone will point Webb at TRES 2b and take the measurement, and when they do, we'll get a clearer picture of what's actually happening in that atmosphere. Until then, TRES 2b sits in the catalogue as an outlier, a planet that absorbs light better than coal, a world that refuses to follow the template, and the fact that it exists at all, that something this dark can form and survive and maintain its strangeness over billions of years, tells us the universe is still holding back, still keeping secrets, still building things we didn't think were possible. And if a planet can be dark enough to vanish, what else is out there that we're not seeing? That question leads us to the next stop. Another planet that breaks the rules, another object that shouldn't exist. But this time, the impossibility isn't about light, it's about state, the physical state of matter itself. We're about to visit a world where the ice burns. We left TRES 2b hanging in space like a hole someone cut out of the universe, swallowing light and refusing to give it back. A planet so dark that standing near it would feel wrong in ways your brain wouldn't know how to process. Darkness is supposed to mean cold, absence of energy. TRES 2b flipped that assumption. It was dark because it was hot, because the heat trapped inside its atmosphere turned it into a black body that absorbed everything and reflected almost nothing. Now we need to talk about a different kind of impossible. Not darkness, not heat alone. A contradiction that operates at the level of basic physics, a place where the words we use to describe matter stop working the way they should. Gliese 436b is a planet where ice burns, not metaphorically, not in some poetic sense, literally. There is water ice inside this planet, solid crystalline water ice, and the temperature of that ice is somewhere north of 400 degrees Celsius, 800 degrees Fahrenheit, hot enough to bake a pizza, hot enough to melt lead. Hot enough that if you touched it, assuming you could somehow reach through the layers of atmosphere and mantle to get to it, you wouldn't feel cold. You'd feel your hand catch fire. And it's ice, actual ice, frozen water, solid, stable, not melting, not boiling. Just sitting there, crystallized into a lattice, doing what ice does, being solid, at a temperature where ice has no business existing. That's the paradox. That's what makes Gliese 436b one of the strangest objects in the exoplanet catalogue. Not the hottest, not the biggest, not even particularly far away. It's only about 32 light-years from Earth, practically next door by astronomical standards. You could point a decent amateur telescope in the general direction of the constellation Leo, and you'd be looking at the right patch of sky. The star it orbits, Gliese 436, is a red dwarf, small, cool, unremarkable. The kind of star that makes up about 70% of the galaxy, and orbiting that star, closer than Mercury orbits our Sun, is a planet that has decided the rules don't apply to it. The discovery happened in 2004, back when exoplanet science was still in its awkward teenage phase. The field was growing fast, new planets were being announced every few months, but the techniques were crude compared to what we have now. Gliese 436b was detected using the radial velocity method. Astronomers measured the tiny wobble in the star's motion caused by the planet's gravity tugging on it as it orbited. The wobble was small but detectable, and the math that fell out of it told a clear story. There was a planet there. It had a mass of roughly 21 to 25 Earth masses, putting it in the same weight class as Neptune. It orbited every 2.64 days, whipping around its star at a distance of about 0.028 astronomical units. For perspective, Mercury orbits at 0.39 astronomical units. Gliese 436b is more than 10 times closer to its star than Mercury is to the Sun. That proximity to its star means heat, lots of it. The dayside temperature of Gliese 436b has been estimated at around 712 Kelvin. In Celsius, that's 439 degrees. In Fahrenheit, 822. The planet is being baked, not to the extremes of Kelt 9b, not anywhere close, but hot enough that water in any normal state should be vapor, superheated steam, gas, not solid. And yet, when scientists modeled the planet's interior, when they tried to figure out what it was actually made of, the numbers kept pointing to the same conclusion: water, lots of it, not on the surface, not as an ocean. Deep inside, compressed under pressures so immense that the normal rules governing phase transitions, the rules that say ice melts when you heat it, those rules get overwritten by something more fundamental: pressure. This is where we need to talk about phase diagrams, because they're the key to understanding how any of this works. A phase diagram is a map. It tells you what state a substance will be in: solid, liquid, or gas, depending on temperature and pressure. For most of human history, we only cared about the phase diagram of water at everyday pressures, the kind of pressures you experience standing at sea level on Earth, 1 atmosphere. At that pressure, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. Simple, intuitive, the foundation of every high school chemistry class. But pressure changes everything. Increase the pressure and the freezing point shifts, the boiling point shifts. Entirely new phases of ice appear, phases that don't exist anywhere on Earth's surface, phases that require pressures found only deep underground or inside the interiors of massive planets. On Earth, the ice you put in your drink is called ice IH. The H stands for hexagonal because the crystal structure is a hexagonal lattice. It's the only kind of ice most people ever encounter. It's stable at normal atmospheric pressure and temperatures below 0 Celsius. Raise the pressure high enough, though, and ice IH stops being stable. It transforms into other forms: ice 2, ice 3, ice V, ice 6, ice 7. Each one has a different crystal structure, and each one is stable in a different region of the phase diagram. Ice 6 and ice 7 are the ones that matter for Gliese 436b. These are high-pressure phases of water ice that remain solid at temperatures far above 0. Ice 6 forms at pressures around 1 gigapascal, roughly 10,000 times atmospheric pressure at sea level, and it stays solid up to temperatures around 80 degrees Celsius at higher pressures. Ice 7 requires even more pressure, starting around 2 gigapascals, and it's stable to much higher temperatures. At 10 gigapascals, ice 7 remains solid past 350 degrees Celsius. At 20 gigapascals, it can survive past 500 degrees Celsius. The exact numbers depend on the pressure, but the pattern is clear. Squeeze hard enough and water stops caring how hot it is. It stays frozen because the molecules are packed so tightly by the pressure that they don't have room to move into a liquid state. The thermal energy is there. The molecules are vibrating, but they're locked in place by the sheer weight of everything above them pressing down. Gliese 436b has that weight. The planet's gravity, roughly 25 times stronger than Earth's at the surface, compresses the interior into a pressure cooker. Models of its internal structure suggest a rocky core at the center, similar to what you'd find inside Earth or Neptune. Surrounding that core is a thick mantle of water, not liquid water, not water vapor, ice, exotic high-pressure ice, Ice 6, Ice 7, possibly even higher pressure phases that don't have convenient names yet. And on top of that ice mantle, a relatively thin envelope of hydrogen and helium, the leftover gas from the planet's formation, heated by the star and slowly leaking into space. The layer of exotic ice is where the strangeness lives. It's not a thin shell. It's a mantle hundreds or thousands of kilometers thick, depending on whose model you trust. The temperature in that mantle climbs as you go deeper, heated by the planet's core and by the residual heat of formation left over from when the planet first coalesced. Near the outer edge, where the pressure is lower, the ice might be in a phase closer to what we'd recognize. Deeper in, the pressure ramps up and the ice transitions into denser, more alien forms. At the very bottom, where the ice mantle meets the rocky core, the pressure could be tens of gigapascals and the temperature could be over 1,000 degrees. And through all of that, the ice stays solid because it has no choice. The pressure won't let it melt. This is not a theoretical curiosity. This is what the data says. The planet's mass and radius, combined with its density, about 1.6 grams per cubic centimeter, tell us it's too light to be made mostly of rock and too heavy to be made mostly of gas. The only way to match the numbers is to fill the interior with something less dense than rock, but denser than hydrogen. Water fits. Water in the form of high-pressure ice fits even better. The models converge on the same picture. Gliese 436b is a Neptune-sized planet with a thick mantle of hot ice wrapped around a rocky core. The term hot ice sounds like an oxymoron. It sounds like something someone made up to sell a science fiction novel. But it's not fiction, it's material science. It's thermodynamics. It's what happens when you take a substance as common as water and subject it to conditions so extreme that it stops behaving the way your everyday experience tells you it should. And the strangest part is that hot ice isn't even rare in the universe. We just didn't know about it until recently because we didn't have a way to study it. Neptune and Uranus, the ice giants in our own solar system, are thought to have interiors filled with hot ice, not at the surface. Their surfaces, if you can call the upper layers of their atmosphere's surfaces, are cold, but deeper down, where the pressure builds, the water that makes up a significant fraction of their mass transitions into high-pressure ice phases. We've suspected this for decades based on models of their internal structure, but we've never been able to confirm it directly because we've never sent a probe deep enough into either planet to measure it. The Voyager 2 flyby in the 1980s gave us pictures and atmospheric data, but it couldn't tell us what was happening thousands of kilometers below the cloud tops. Gliese 436b is different. It's smaller than Neptune, it's closer to its star, and because it transits, because it passes in front of its star from our perspective, we can study it in ways we can't study Neptune. Every time the planet crosses the star, light from the star passes through the planet's atmosphere before reaching our telescopes. By analyzing that light, by looking at which wavelengths get absorbed and which pass through, we can build a chemical profile of the atmosphere, and that profile tells us about the planet's composition. The early observations, made with space telescopes like Spitzer and Hubble, found water vapor in the atmosphere. Not surprising for a planet thought to be rich in water. They also found evidence of methane, carbon monoxide, and other molecules that suggested the atmosphere was being stirred by complex chemistry driven by the heat from the star. But the real insight came from combining the atmospheric data with models of the interior. The atmosphere is light, mostly hydrogen and helium. The planet as a whole is denser. That density has to come from deeper down, from the mantle, from the layer of exotic ice. The more scientists studied Gliese 436b, the more they realized it was a window into a type of planet that's probably common in the galaxy, but that we'd never been able to study up close. Hot Neptunes, worlds with masses between Earth and Neptune, orbiting close to their stars, heated to temperatures that make their surfaces uninhabitable, but not hot enough to strip away their atmospheres entirely. These planets don't exist in our solar system. The closest analog is Neptune, but Neptune is cold and far from the Sun. Gliese 436b is what Neptune would look like if you moved it inward, cranked up the heat, and watched the outer layers start to peel away. And that's the other thing about Gliese 436b. It's not stable, not in the long term. The planet is losing mass, slowly, gradually, but measurably. Observations in the ultraviolet spectrum have detected a cloud of hydrogen gas surrounding the planet, extending far beyond its physical radius. The gas forms a tail, like the tail of a comet, stretching out behind the planet as it orbits. The tail is enormous. It's been described as immense in some of the literature, and for good reason. The hydrogen cloud extends for millions of kilometers, far enough that it's visible in ultraviolet light, even from 32 light-years away. The source of that hydrogen is the planet's atmosphere. The star, Gliese 436, is bombarding the planet with ultraviolet radiation. Not as intense as the radiation from a hotter star, but enough to strip hydrogen atoms from the outer layers of the atmosphere and blow them into space. The process is called atmospheric escape, and it's the same process that's happening to Kelt 9b and other hot Jupiters. The difference is that Gliese 436b is smaller, its gravity is weaker. The hydrogen it's losing represents a larger fraction of its total atmospheric mass. Over millions of years, this process could strip away the entire hydrogen-helium envelope, leaving behind just the ice mantle and the rocky core. What you'd be left with is something that looks less like a Neptune and more like a giant water world, a super-Earth made mostly of water ice. That transformation hasn't happened yet. The process is slow. Current estimates suggest the planet is losing mass at a rate of a few hundred tons per second. That sounds like a lot, and it is if you're measuring it in human terms. But compared to the planet's total mass, which is about 130 trillion kilograms, it's negligible. At the current rate, it would take hundreds of billions of years to strip away the entire atmosphere. The planet has time, but the fact that the process is happening at all tells us something important. Gliese 436b is in transition. It's not a finished product. It's a world caught in the middle of its evolution, and we're watching it change in real time. The comet-like tail is one of the most striking visual features of Gliese 436b, even though we can't see it with the naked eye. If you could observe the planet in ultraviolet light from a spacecraft nearby, it wouldn't look like a sphere. It would look like a sphere trailing a glowing cloud of gas stretched out along its orbit, painting a faint line across the sky behind it. The hydrogen in that tail is escaping the planet's gravity well, but not the star's. It's still bound to the star, orbiting alongside the planet, slowly drifting outward under the pressure of the stellar wind. Eventually, over timescales measured in millions of years, the hydrogen will disperse completely, mixed into the surrounding interstellar medium. The planet's atmosphere will shrink, the hydrogen-helium envelope will thin, and what remains will be heavier, denser, more dominated by water. The implications of Gliese 436b go beyond just this one planet. If hot ice can exist inside a planet this small, this close to its star, then it's probably common. Every hot Neptune we've found, and there are dozens of them in the exoplanet catalogue, is a candidate for having a similar interior structure: a rocky core, a mantle of high-pressure ice, a thin outer envelope of gas. The exact proportions vary depending on the planet's mass, its distance from its star, and its formation history, but the basic template is the same: water compressed by gravity into solid phases that don't exist on Earth, heated by the star and by internal processes, trapped inside a planet that's too small to hold on to its lightest elements, but too big to let the ice melt. And this matters for how we think about water in the universe. For most of human history, water meant liquid. Oceans, rivers, rain. Ice was something that happened when water got cold. Steam was what happened when it got hot. The idea that water could exist in a dozen different solid phases, each one stable under specific combinations of temperature and pressure, each one with its own crystal structure and physical properties, that was a revelation that came out of laboratory experiments in the 20th century. Scientists squeezed water in diamond anvil cells, tiny devices that can generate pressures equivalent to the deep interiors of planets, and discovered that water is far more complicated than anyone expected. Gliese 436b is the laboratory experiment scaled up to planetary size. It's proof that the exotic phases of water, predicted by theory and created in labs, actually exist in nature. They're not laboratory curiosities, they're a common feature of planetary interiors. And if they're common, then our models of how planets form, how they evolve, how they transport heat, all of those models need to account for the fact that water isn't just water, it's a shapeshifter, a substance that changes its properties depending on where it is and what's happening around it. There's another layer to this. The existence of hot ice inside planets like Gliese 436b raises questions about habitability. Not habitability on Gliese 436b itself. That ship sailed the moment the planet migrated inward and turned into a scorched Neptune. But habitability in general. If a planet can have a thick mantle of hot ice, what does that mean for heat transport, for volcanic activity, for the magnetic fields that protect a planet's atmosphere from stellar wind? Water, in its various forms, plays a role in all of those processes. On Earth, water lubricates plate tectonics. It lowers the melting point of rock in the mantle, making it easier for material to flow and for tectonic plates to slide past each other. Without water, Earth's surface would be a static shell. No earthquakes, no volcanoes, no recycling of carbon between the atmosphere and the interior. The climate would be different, possibly uninhabitable. Water in the mantle is one of the reasons Earth is the way it is. Now imagine a planet with a mantle made entirely of water. Not liquid water mixed into rock, but solid water ice forming the bulk of the mantle. How does heat move through that? How does the planet cool? Does the ice flow like Earth's mantle flows, driven by convection currents that carry heat from the core to the surface? Or does it stay rigid, locking the heat inside? The answers depend on the pressure, the temperature, the exact phase of ice, and the presence of impurities mixed into the ice. We don't know yet. The models are still being built. But the questions are important because if water-rich planets are common, and the data from exoplanet surveys suggests they are, then a lot of planets in the galaxy might have interiors that look more like Gliese 436b than like Earth. And if their interiors are different, their surfaces might be different too. Their atmospheres might evolve differently. Their ability to host liquid water on the surface, the one ingredient we're most confident is necessary for life, might depend on processes happening deep inside the planet that we're only just beginning to understand. Gliese 436b is teaching us that water is more versatile than we gave it credit for. It's not just the stuff of oceans and rain clouds. It's a structural material, a building block of planetary interiors, a substance that can remain solid at temperatures that would boil your blood and can remain liquid at pressures that would crush steel. The phase diagram of water is a map of possibilities, and we're only now starting to explore the far corners of that map where the conditions are extreme and the outcomes are strange. The discovery of hot ice inside Gliese 436b also highlights how much we still don't know about planets in general. For decades, planetary science was built on a sample size of 8, 9 if you counted Pluto before it got reclassified. Our theories of how planets form, how they're structured, how they evolve, all of it was based on the planets in our solar system. And those planets, while diverse, represent a narrow slice of what's possible. We have rocky planets close to the Sun, gas giants far from the Sun, ice giants in between, no hot Neptunes, no super-Earths, no planets with thick mantles of exotic ice. The solar system, for all its wonders, is not a complete catalogue of planetary types. It's a sample, a biased sample. And every time we find a planet like Gliese 436b, a planet that doesn't fit the template, we're forced to expand our understanding of what planets can be. The physics of hot ice is settled. We know it exists. We know the conditions required to create it. We can reproduce those conditions in labs and measure the properties of the ice directly. The uncertainty is in the details. How thick is the ice mantle on Gliese 436b? Exactly what phase of ice dominates at different depths? How much heat is flowing through it? How fast is the planet cooling? Those questions require better data, longer observations, more detailed models. The James Webb Space Telescope will help. Webb can analyze the atmospheres of planets like Gliese 436b with unprecedented precision, picking apart the chemical composition and searching for clues about what's happening beneath the surface. Future space missions, dedicated to studying exoplanets up close, will help even more. But the broad strokes are already clear. Gliese 436b is a planet with a burning heart of ice, a world where water has been forced into a state that defies intuition. And it's not alone. The universe is full of contradictions, full of places where the rules we learnt in school stop applying, where ice burns, where light vanishes, where stars turn into objects smaller than cities. Gliese 436b is one of those contradictions. A reminder that matter, under the right conditions, can do things we didn't think were possible. And the universe has no shortage of extreme conditions: high pressure, high temperature, high gravity, low gravity, intense radiation, perfect vacuum. Every combination produces different outcomes, different phases, different behaviors. We're cataloging those outcomes now, planet by planet, system by system. Each one teaches us something new about the boundaries of what's possible. Each one pushes the edges of the phase diagrams we drew based on experiments conducted in comfortable laboratories on a comfortable planet orbiting a comfortable star. Gliese 436b taught us that water doesn't have to be wet. It doesn't have to be cold. It just has to be under enough pressure. And if pressure can keep ice solid at 800 degrees, what else can it do? What other materials, under what other conditions, are waiting in the interiors of planets we haven't studied yet? Those are questions for the next generation of telescopes, the next generation of models, the next wave of discoveries that will inevitably find something even stranger than hot ice. Something that makes us rewrite the textbooks again, because that's what exploration does. It finds the exceptions, the outliers, the things that shouldn't exist but do. And now that we've seen a planet held together by gravity and heat, orbiting a star, locked in a predictable pattern, we need to talk about the opposite: planets with no stars at all, worlds that were kicked out of their birth systems and sent tumbling into the void, orphans, wanderers. planets drifting alone through the dark, with no sun to warm them and no orbit to guide them home. We left Gliese 436b locked in orbit around its star, trapped in a prison of gravity and heat, its interior filled with ice that refuses to melt, despite temperatures that would bake bread. A world caught in contradiction, held together by the same force that keeps Earth spinning around the Sun. Orbital mechanics, the ancient dance between a planet and the star that birthed it. A relationship measured in gravitational pull and angular momentum, predictable enough that you can calculate where a planet will be 1,000 years from now, with nothing more than basic physics and a calculator. That relationship, that gravitational tether between planet and star, is the foundation of every planetary system we've ever studied. Planets orbit stars. That's what makes them planets. The word itself comes from the Greek word for wanderer, but even the ancient Greeks understood that the wandering followed patterns, cycles, predictable paths across the sky. The planets wandered, yes, but they always came back. They were bound. Now we need to talk about the ones that aren't. There are planets out there, real planets with mass and gravity and possibly atmospheres, drifting through interstellar space with no star to orbit, no sun in their sky, no light warming their surfaces, no gravitational anchor holding them in place. They were born in planetary systems like ours, formed from the same swirling disks of gas and dust that built Earth and Jupiter and every other world we've catalogued. But something went wrong. A gravitational interaction, a close encounter, a collision. Something violent enough to break the bond between planet and star and fling the planet outward into the void at escape velocity. And once a planet reaches escape velocity, once it crosses that threshold where the star's gravity can no longer pull it back, it's gone. It becomes a wanderer in the truest sense, a rogue. Astronomers call them rogue planets, free-floating planets, orphans. The terminology varies depending on who you ask and what conference they last attended, but the concept is the same, a planet with no star. A world adrift in the space between solar systems, traveling alone through the dark, with no destination and no way home. The existence of rogue planets has been theorized for decades, but finding them is a different problem entirely. Most of our exoplanet detection methods rely on the presence of a star. The transit method requires a planet to pass in front of its star, blocking a tiny fraction of the light. The radial velocity method measures the wobble a planet induces in its star's motion. Direct imaging works by blocking out the star's light, so you can see the much dimmer planet beside it. All of these techniques have one thing in common. They need a star. Without one, the planet is invisible, or nearly invisible. A cold, dark object drifting through space, emitting no light of its own, reflecting no light because there's nothing to reflect. It's a ghost. The only reason we can detect rogue planets at all is that some of them are young enough that they still retain heat from their formation. When a planet forms, the process is violent. Gas and dust collide, clump together, compress under their own gravity. That compression generates heat, a lot of it. For the first few million years of a planet's life, it glows with thermal radiation left over from its birth, not visible light. The planet isn't hot enough for that, but infrared, heat. And if you point an infrared telescope at a patch of sky, and you see a point of heat that isn't associated with any star, that's moving through space on its own trajectory, that has the right mass to be a planet, you've found a rogue. That's how PSOJ 318.522 was discovered. A young Jupiter-sized object glowing faintly in the infrared, drifting through space about 80 light-years from Earth, with no star anywhere near it. The discovery came in 2013. A team of astronomers led by Michael Liu at the University of Hawaii was conducting a survey called the Pan-STARRS-1 survey, looking for brown dwarfs. Brown dwarfs are objects that fall into the gap between planets and stars. Too massive to be planets, not massive enough to sustain hydrogen fusion and become true stars. They are sometimes called failed stars, which feels a little harsh, but the name stuck. Brown dwarfs are relatively common, and they emit enough infrared radiation that they're easier to detect than rogue planets. The survey was designed to find them, catalog them, and study their properties. PSOJ 318.522 showed up in the data as an infrared source moving across the sky. At first, it looked like a brown dwarf, the right color, the right brightness. But when the team analyzed the spectrum, the light broken down into its component wavelengths, something didn't match. The spectrum showed features consistent with a much younger object, and young brown dwarfs are rare because brown dwarfs cool quickly. Within a few tens of millions of years, most of them fade into the infrared background and become hard to detect. This object, whatever it was, appeared to be extremely young, maybe 12 million years old, maybe less. And its mass, estimated from its brightness and temperature, came in at only about 6 to 7 times the mass of Jupiter. That's not a brown dwarf, that's a planet, a gas giant, free-floating, no star. The announcement made headlines, not because rogue planets were a new idea, but because this was one of the cleanest examples anyone had found. PSOJ 318.522 wasn't hiding in the glare of a nearby star. It wasn't ambiguously straddling the line between planet and brown dwarf. It was clearly planet mass, clearly alone, and clearly young enough to still be glowing. For the first time, astronomers had a rogue planet they could study in detail. They could take spectra, measure its temperature, estimate its mass, track its motion through space. And all of that data pointed to the same conclusion. This was a planet, and it had no home. The question everyone asks when they hear about rogue planets is, how does a planet end up alone? The answer comes in 2 flavors, and both are violent. The first possibility is ejection. Planetary systems are not static, they're dynamic, chaotic environments where gravity plays out on timescales ranging from days to millions of years. When a planetary system is young, before the orbits have settled into stable configurations, planets interact, they tug on each other. They exchange energy, and sometimes those interactions lead to close encounters. 2 planets pass near each other, close enough that their gravitational fields overlap. One of them gets a boost of energy, its orbit expanding outward. The other loses energy, its orbit shrinking inward. This process is called gravitational scattering, and it's messy. The planet that gains energy can gain enough to escape the star's gravity entirely. It gets flung outward, faster and faster, until it crosses the escape velocity threshold and breaks free. The planet that loses energy spirals inward, possibly colliding with the star, possibly colliding with another planet, possibly settling into a closer but stable orbit. Either way, the system loses a planet. The ejected planet becomes a rogue. This mechanism is thought to be common, especially in systems with multiple gas giants. Gas giants are massive enough to gravitationally bully each other. If 2 or more gas giants form in the same system and their orbits are close enough to allow interactions, the system becomes unstable. Something has to give. One planet gets ejected, maybe more than one. The survivors settle into stable orbits and the system calms down, but the ejected planet is gone. It's traveling through space at tens of kilometers per second, fast enough that the star's gravity can never pull it back. It's on its own. Computer simulations of planetary system formation show that ejections are not just possible, they're expected. Some models suggest that for every planetary system that stabilizes, 1 or more planets get thrown out. If that's true, and the evidence is pointing in that direction, then there could be more rogue planets in the galaxy than there are stars, billions of them, maybe tens of billions. An entire population of orphaned worlds drifting through the void, invisible unless they're young enough to still glow, or unless they happen to pass close enough to a star that their gravity causes a detectable effect. The second possibility is that some rogue planets never had a star to begin with. This idea is more controversial because it blurs the line between planet and brown dwarf. The standard definition of a planet is that it forms in a protoplanetary disk around a star. A brown dwarf forms the same way a star does, from the direct collapse of a gas cloud. The distinction is about formation mechanism, not mass. But out in the field, that distinction gets hard to enforce. If a small gas cloud collapses on its own and forms an object with the mass of a planet, is it a planet or a brown dwarf? Different astronomers will give you different answers. What we do know is that star formation is inefficient. When a giant molecular cloud collapses, it fragments into smaller pieces. Most of those pieces become stars. Some become brown dwarfs, and the smallest fragments, the ones that barely have enough mass to collapse at all, might form objects in the planetary mass range. These objects are sometimes called sub-brown dwarfs, or planetary mass objects. They're not orbiting anything, they formed on their own, and from a distance they look exactly like rogue planets. PSOJ 318.522 could be either. It could be a gas giant that formed around a star and got ejected, or it could be a planetary mass object that formed independently. The data doesn't tell us which. What it does tell us is that the object is young, it's alone, and it's glowing. The surface temperature is estimated at around 1,100 degrees Celsius, hot enough to emit a dull red glow if you could see it with human eyes. But there's no star nearby to illuminate it, no reflected light. Just the faint heat of its own formation radiating into the emptiness of space. Imagine that for a moment. A gas giant the size of Jupiter, floating in interstellar space with no sun, no planets nearby, no moons, nothing, just the object and the void. The closest star might be light years away, a faint point of light, no brighter than any other star in the sky. If you could somehow stand on a solid surface in the upper atmosphere of PSOJ 318.522, which you couldn't because it's a gas giant, but if you could, the sky would be black, not the black of a moonless night on Earth where you can still see stars, proper black. The kind of black you get in deep space, where the stars are so far away and so dim that they barely register against the background. And the temperature, despite the planet's internal heat, would be dropping, slowly, year by year. The planet is cooling. It has no star to replenish the energy it's radiating away. Every joule of heat it emits into space is gone forever. And over millions of years, over tens of millions of years, the glow will fade, the surface temperature will drop, the planet will cool until it's indistinguishable from the interstellar medium, and at that point it becomes effectively invisible. A cold, dark ball of gas drifting through the galaxy, undetectable unless it happens to pass directly in front of a background star and causes a microlensing event. That fading, that slow death by cooling, is the fate of every rogue planet. They're living on borrowed time. The heat they were born with is all they have. There's no star to keep them warm, no tidal heating from a nearby gas giant, no radioactive decay in a rocky core because most of them don't have rocky cores. They're gas, and gas cools, not quickly by human standards. PSOJ 318.522 will probably remain detectable for another few tens of millions of years. But on cosmic timescales, that's nothing. The planet is 12 million years old now. In another 100 million years, it will be dark, silent, a relic drifting through space with no way to announce its presence. The loneliness of a rogue planet is hard to overstate. We are used to thinking of planets as part of systems. Earth has the Sun. The Sun has 8 planets, a handful of dwarf planets, an asteroid belt, a Kuiper belt, countless comets and moons. The solar system is crowded, busy, full of things moving, interacting, orbiting. A rogue planet has none of that. It's alone in the most literal sense. The nearest object with any mass might be a light year away. It's traveling through space at tens of kilometers per second, but on interstellar scales that's slow. It would take tens of thousands of years just to cover the distance from the Sun to the nearest star. And in all that time, nothing changes. No sunrise, no sunset, no seasons. No weather driven by solar heating. Just the planet and the dark. Some astronomers have speculated that rogue planets could, in theory, support life. Not on their surfaces. The surfaces, or rather the upper atmospheres, are far too cold once the initial heat from formation radiates away. But deeper down, in the interior, the pressure keeps things warm. And if a rogue planet has a moon, the tidal heating generated by the gravitational interaction between the planet and the moon could keep the moon warm. Europa is kept warm by tidal heating from Jupiter. A rogue planet with a large moon could maintain the same process even without a star. The moon would have liquid water beneath an icy crust, heated by the flexing of its interior as it orbits the planet. Life, if it could start in that kind of environment, would never see a sun. It would never have access to photosynthesis. It would have to rely entirely on chemical energy from hydrothermal vents, the same way life in Earth's deep oceans relies on chemosynthesis at hydrothermal vents far below the reach of sunlight. It's possible, maybe even plausible, but undetectable with current technology. A biosphere on a moon orbiting a rogue planet would be invisible. We wouldn't find it unless we happened to send a probe directly to it, and the odds of that are vanishingly small. The detection of PSO J318.522 opened a door. It proved that rogue planets are out there, and that at least some of them are young enough to find. Since 2013, more candidates have been identified, some confirmed, some still ambiguous. The numbers are hard to pin down because the definition of a rogue planet is still being argued over in the literature. Does it have to form in a planetary system and get ejected, or do planetary mass objects that form independently count? The International Astronomical Union, the group responsible for defining these things, hasn't settled the issue yet. But regardless of the terminology, the objects exist. Planet mass bodies with no stars, free-floating, alone. Some estimates suggest there could be twice as many rogue planets in the Milky Way as there are stars. Other estimates push that number even higher. The logic is straightforward. Every planetary system that forms probably ejects at least one planet during its early chaotic phase. The galaxy has somewhere between 100 and 400 billion stars. If even a fraction of those stars formed with planetary systems that ejected a planet, you end up with tens of billions of rogues, maybe hundreds of billions, a hidden population of dark worlds that we've only just started to detect. The implications are strange. We think of the galaxy as a collection of solar systems, stars with planets, light and gravity holding everything together in predictable patterns. But if the majority of planets don't orbit stars, if the majority are drifting alone through interstellar space, then the picture changes. The galaxy isn't a collection of solar systems, it's a sea of darkness punctuated by islands of light. And between those islands, in the vast empty stretches of space, there are worlds, cold worlds, dead worlds, worlds that lost their stars and kept moving. The idea has a kind of existential weight to it. A planet is supposed to have a place, a role, an orbit. Rogue planets have none of that. They're cosmic orphans, refugees from systems that destroyed themselves or tore themselves apart in the chaos of formation. They're the ones that got away, but what they got away to is worse. Eternal night, no destination, no future except a slow fade into the cold. PSOJ 318.522 is still out there right now. It's still moving, still glowing faintly in the infrared, still alone. In another few million years, it will be too cool to detect with current instruments. It will slip below the threshold of detectability and disappear from our catalogues. Not because it stopped existing, just because we stopped being able to see it, and it will keep drifting through the Milky Way, past other stars, past other planetary systems. A silent witness to everything around it, but never part of any of it. Never captured by another star's gravity, never pulled into an orbit, just moving forever. There's a thought experiment astronomers sometimes use to illustrate the scale of interstellar space. If the sun were the size of a basketball, Earth would be a grain of sand about 25 meters away. Jupiter would be a marble about 130 meters away. And the nearest star, Proxima Centauri, would be another basketball 6,700 kilometers away. That's the distance from New York to London. That's how much empty space there is between stars, and somewhere in that emptiness, drifting through the nothing, are planets. Worlds that were born in systems like ours and then cast out into the void. Worlds that are moving through the dark with no reference point, no landmark, no way to know if they're headed anywhere because there's nowhere to head. Space doesn't have destinations unless you create them. And a rogue planet has no ability to create anything. It just drifts. The discovery of rogue planets forces a reckoning with the idea that planets are rare or special. We used to think Earth was unique. Then we found other planets in the solar system and realized Earth was one of several. Then we found exoplanets and realized planets are common. Now we're finding that some planets don't even need stars. They exist on their own. And if that's true, if rogue planets outnumber stars, then the universe is even more crowded than we thought. Not with life, not with light, but with matter, with mass. With objects that have enough gravity to be round, enough size to be called worlds, but none of the structure or stability that makes a world seem like a place. And the strangest part is that we're only seeing the tip of the population. The ones we've detected are the young ones, the ones still glowing, the ones that happen to form recently enough that they haven't cooled to invisibility yet. But for every young rogue planet we've found, there are probably dozens or hundreds or thousands of older ones that formed billions of years ago and have long since gone dark. They're still out there, still drifting, still moving through the galaxy. We just can't see them. They're ghosts in the most literal sense, present but undetectable, invisible but real. The next generation of infrared telescopes, including the Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will be more sensitive than anything we've built before. Roman will be able to detect cooler, older rogue planets that current instruments miss. It will survey large areas of the sky, looking for faint infrared sources that move independently of any star. The expectation is that Roman will find hundreds of rogue planets, maybe thousands, and when it does, we'll get a clearer picture of how common they really are. Whether the high-end estimates are correct, whether the galaxy really is filled with dark wandering worlds, or whether the ones we've found so far are outliers. PSOJ 318.522 is the prototype, the first clear example, the case study that proved rogue planets are real and that we can find them if we look carefully enough. But it's not the end of the story, it's the beginning. The first chapter in what's likely to be a much longer book about a population of planets we didn't know existed until a decade ago. Planets with no stars, no orbits, no future except the slow march toward absolute cold, the universe's ultimate loners. And the uncomfortable truth is that every planetary system we've studied, including our own, probably ejected at least one planet during its formation. Somewhere out there, drifting through the Milky Way, there might be a planet that used to orbit the Sun. A world that formed in the same protoplanetary disk that built Earth and Jupiter and Mars. A sibling we lost before we ever knew it existed. It could be light years away by now, traveling through interstellar space with no way back. A piece of the solar system's history, erased by a gravitational interaction we'll never be able to reconstruct. If that planet exists, if it's out there, we'll probably never find it. It's too far away, too cold, too dark. But the possibility sits in the back of the data, like a footnote no one wants to read. The solar system might not have always been 8 planets. It might have been 9 or 10 or more. And the ones that didn't make it became rogues. Rogue planets are a reminder that stability is not guaranteed. That the systems we see today, the ones with planets in neat, predictable orbits, are the survivors. The ones that made it through the chaos of formation without tearing themselves apart. But for every system that stabilized, there are planets that didn't survive. Worlds that got flung into the dark and never looked back. And they're still out there, moving, alone, invisible. The loneliness of a rogue planet is absolute. No star will ever rise on its horizon. No moon will ever orbit it, unless it brought one with it when it was ejected. No asteroid will ever impact its surface, because there are no asteroids in interstellar space. It's just the planet and the void. And the void is patient, it waits. And eventually, the planet cools, the glow fades, the last trace of warmth radiates away into the nothing. And what's left is a cold, dark sphere of gas, or rock, or ice, indistinguishable from the emptiness around it, a world that exists but cannot be seen, a planet that has no story because there's no one to tell it, and yet the universe built them, billions of them, maybe more. Scattered through the galaxy like seeds that never found soil, and every one of them is a reminder that not every planet gets a happy ending. Not every world gets to orbit a star for billions of years in the kind of stable, predictable environment that allows oceans and atmospheres and possibly life to develop. Some planets lose, they get kicked out. And once they're out forever. There's no coming back, no second chance, just the endless drift through space with no destination and no hope of arrival. PSOJ 318.522 is one of those planets, and it's been drifting for 12 million years. And it will keep drifting, and one day, millions of years from now, it will be cold and dark and invisible, and it will still be moving. And no one will ever know it's there unless we get extraordinarily lucky and it passes directly between us and a distant star, briefly bending the star's light in a micro-lensing event that lasts a few hours. That's the only way we'll detect the old ones, the ones that have been drifting for billions of years. A brief flicker in a telescope, a momentary distortion of light, and then it's gone, back into the dark. That's the fate of a rogue planet, to exist in a state of permanent isolation, to move through the universe without ever being part of it. To be a world without a system, a planet without a star, a place that is nowhere. And the universe has built billions of them, and most of them we'll never see. But now that we know they're out there, now that we've confirmed their existence and started counting them, the galaxy feels different, bigger, darker, more crowded with things we can't see. And the question shifts from whether rogue planets exist to how many there are and what else we're missing. Because if the space between stars is full of dark, wandering worlds, what else is out there that we haven't noticed yet? What other populations of objects are drifting through the void, invisible, undetectable, present but unknown? And as our instruments improve, as our surveys get deeper and more sensitive, what are we going to find next that forces us to redraw the map again? That's where we're headed, not back to the warmth of stars and stable orbits, but forward into the catalogue of impossible things. Planets that shouldn't exist but do, worlds that break the rules in ways we're still trying to explain. We've seen heat, we've seen darkness, we've seen ice that burns and planets with no stars, and we're not done yet. There are more, stranger ones. Worlds that make the ones we've covered so far look almost reasonable by comparison, and it's time to meet them. We left PSOJ 318.522 drifting alone through the void, a gas giant orphaned from whatever system gave it birth, glowing faintly in the infrared as it cools toward invisibility, a planet with no star, no orbit, no future except the long, slow fade into the cold. The loneliness of a rogue planet is absolute, and the universe has built billions of them, maybe more, an entire hidden population of worlds we only started counting a decade ago. But rogue planets, for all their strangeness, are at least comprehensible. They follow the rules. Gravity, thermodynamics, orbital mechanics. The rules worked, and then something broke the rules, and the planet got ejected. Cause and effect. We understand the mechanism, even if the outcome is unsettling. A rogue planet is what happens when the dice come up wrong during planetary formation. It's rare, but not impossible. Violent, but predictable once you know the history. The planets we're about to discuss don't fit that pattern. They're not edge cases. They're not outliers that got unlucky. They're planets that shouldn't exist in the first place. Planets whose very presence in the configurations we observe them in contradicts the models we built to explain how planets form. And the more we look, the more of them we find. The list of impossible planets isn't shrinking, it's growing. Every year, sometimes every month, a new discovery lands in the journals and forces another revision to what we thought we understood. The edges of the possible keep expanding, and every time they expand, they reveal something stranger than what came before. Let's start with WASP-17b because it represents a specific flavor of wrongness that took astronomers years to accept. WASP-17b is a gas giant orbiting a star in the constellation Scorpius, about 1,300 light-years from Earth. It's big. Roughly twice the diameter of Jupiter, which makes it one of the largest exoplanets ever discovered. Puffy is the word that shows up in the literature. Its density is so low, around 0.19 grams per cubic centimeter, that it would float in water if you could find a bathtub large enough to hold it. For context, Jupiter's density is 1.33 grams per cubic centimeter. Saturn, the least dense planet in our solar system, sits at 0.69. WASP-17b is less dense than cork. The size and fluffiness are interesting, but they're not the problem. Hot Jupiters get puffy. The intense radiation from their nearby stars heats the atmosphere, causing it to expand. WASP-17b orbits close to its star, completing one orbit every 3.7 Earth days, so the puffiness makes sense. The problem is the direction it's orbiting. WASP-17b orbits backward. Not backward in the sense that it's moving the wrong way around the star. Backward in the sense that it's orbiting in the opposite direction of the star's rotation. The star spins one way, the planet orbits the other way. This is called a retrograde orbit, and in the context of planetary formation, it's not supposed to happen. Here's why. Planets form in a protoplanetary disk, a flat spinning cloud of gas and dust surrounding a young star. The disk spins in the same direction the star spins because both the disk and the star formed from the same collapsing gas cloud. Conservation of angular momentum, Physics 101. The material in the disk gradually clumps together into planets, and those planets inherit the disk's rotation. They orbit in the same direction the star spins because that's the direction everything was already moving. Prograde orbits, the default, the expected outcome. Every planet in our solar system orbits the Sun in the same direction the Sun spins. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all prograde. It's not a coincidence. It's a direct consequence of how the solar system formed. WASP-17b is orbiting the wrong way. The star is spinning. The planet is going the other direction. That doesn't happen if the planet formed peacefully in a disk and stayed where it formed. Something violent happened. Something that flipped the planet's orbit or forced it into a configuration that standard disk formation models can't produce. The leading explanation involves gravitational interactions with other planets. If WASP-17b formed in a system with multiple gas giants, a close encounter could have altered its orbit, not just moved it inward, the way migration explains hot Jupiters, but flipped it, twisted the orbital plane until the planet ended up moving retrograde. The math works. Computer simulations show that gravitational scattering between planets can produce retrograde orbits, but the process is chaotic, unpredictable, and it requires a specific sequence of events that has to unfold in just the right way to avoid ejecting the planet entirely. Most planets that undergo scattering events don't end up in retrograde orbits. They end up as rogues. WASP-17b managed to avoid that fate, barely. The other possibility, which some models favor, involves the star itself. If the star's rotation axis is tilted relative to the protoplanetary disk, which can happen if the system experienced external perturbations during formation, the planet's orbit might appear retrograde from our perspective, even though it formed prograde relative to the disk. The distinction is subtle and depends on how you measure angles and reference frames, but the bottom line is the same. WASP-17b's orbit is misaligned with its star's rotation in a way that suggests the system's history was violent. Disks don't tilt themselves. Something external pushed them. A passing star, maybe. A close encounter with another system. Something that disrupted the orderly formation process and left behind evidence in the form of a planet orbiting the wrong way. WASP-17b was discovered in 2009 during the Wide-Angle Search for Planets survey, one of the ground-based programs that preceded the Kepler mission. The retrograde orbit wasn't confirmed until follow-up observations measured the Rossiter-McLaughlin effect, a subtle shift in the star's spectrum caused by the planet passing in front of it. The effect tells you the angle between the planet's orbital plane and the star's equator. For WASP-17b, that angle came back at roughly 150 degrees. A prograde orbit would measure close to 0 degrees. 150 degrees means the planet is moving almost directly opposite the star's rotation, not slightly tilted, not moderately inclined, backward. The announcement caused a stir, not because retrograde orbits were thought to be impossible, but because this was one of the first clear examples, and it raised an uncomfortable question. If one planet can end up in a retrograde orbit, how many others are out there that we haven't detected yet? Do most hot Jupiters form peacefully and migrate inward, or do a significant fraction of them arrive at their current positions through violent scattering events that scramble their orbits? The answer matters because it changes the story of how planetary systems evolve. A peaceful migration is one thing. A chaotic scattering event that flips orbits and ejects planets is something else. One produces stable systems with predictable outcomes. The other produces a mess. Since WASP-17b, astronomers have found more planets with retrograde orbits: HATP-7b, HATP-14b, Kepler-25c. The list is growing. None of them should be where they are, moving the way they're moving, if planetary formation followed the textbook script. And the fact that we keep finding them suggests the textbook script is wrong, or at least incomplete. Planets don't always form and stay put. Sometimes they get thrown around. Sometimes they end up in configurations that look impossible until you realize the system's history was more violent than anyone expected. WASP-17b is still there, still orbiting its star backward, still defying the rules every 3.7 days, a gas giant the size of twice Jupiter, floating in space like a balloon, moving in the wrong direction, and no one can say with absolute certainty how it got that way. The best we can do is point to models and simulations and say this could have happened, or maybe that could have happened, and hope future observations narrow the possibilities. Now let's talk about diamonds, because the universe apparently decided that planets made of rock and ice and gas weren't strange enough. There's a category of hypothetical planets called carbon planets, sometimes called diamond planets in the popular press, and the name is not an exaggeration. These are worlds where carbon, rather than silicon and oxygen, dominates the chemistry. And under the right conditions, extreme pressure and high temperature, carbon doesn't stay as graphite or organic compounds. It crystallizes into diamond, not small diamonds, not gemstones, entire planetary interiors potentially made of solid diamond. The concept comes from basic chemistry. Most planets, including Earth, are made primarily of silicates. Silicon and oxygen bonded together into minerals like quartz, feldspar, olivine. The mantle, the crust, the rocks you see on the surface, all silicates. Carbon exists, obviously. It's in the atmosphere as carbon dioxide. It's in the crust as carbonates. It's in living organisms, but it's a trace element, a minor player in the overall composition. Earth's carbon budget is a rounding error compared to the amount of silicon and oxygen, but stars vary in composition. Some stars are more carbon-rich than others, and if a planet forms around a carbon-rich star in a protoplanetary disk where the ratio of carbon to oxygen is higher than it is in our solar system, the chemistry changes. Silicon and oxygen still bond, but there's not enough oxygen to go around. Carbon becomes more abundant, and carbon, under pressure, can form structures that silicon can't, like diamond. The most famous example, the one that gets cited in almost every popular article about diamond planets, is PSRJ 1719-1438b. It's not an exoplanet in the traditional sense. It's the remnant core of a white dwarf star that's been stripped down to a dense crystalline object orbiting a pulsar. The pulsar, a rapidly spinning neutron star, is what's left after a massive star went supernova. The companion object, PSRJ 1719-1438b, is what's left after the pulsar's intense radiation and gravity stripped away the outer layers of a white dwarf that used to orbit it. What remains is a core made primarily of carbon and oxygen, compressed to densities higher than anything found on Earth, and crystallized into what is likely a diamond structure. The object has roughly the mass of Jupiter, but the diameter of a small planet, about 5 times the size of Earth. It orbits the pulsar every 2 hours and 10 minutes, so close that the orbital radius is less than the distance from Earth to the Moon. The phrase diamond planet gets thrown around loosely in the press, and it's worth being precise about what that means. PSRJ 1719-1438b is not a planet someone could land on and mine for diamonds. It's a stellar remnant, a dead star's core. The surface gravity is immense, the environment is hostile, The radiation from the pulsar is lethal, but the composition, the crystalline carbon structure, that part is likely real. And if a stellar remnant can be made of diamond, the question naturally arises whether a planet, a real planet that formed from a protoplanetary disk rather than the death throes of a star, could have a similar composition. The answer is maybe. If a planet forms in a carbon-rich environment, the mantle could be dominated by carbon compounds rather than silicates, carbidies instead of oxides, and under the pressures found deep inside a super-Earth or a Neptune-sized world, some of that carbon could crystallize into diamond. Not the entire planet. The atmosphere would still be hydrogen and helium, or nitrogen, or carbon dioxide, depending on the temperature and the planet's history. The core might still be iron and nickel, but the mantle, the thick layer between the core and the atmosphere, could be diamond. Kilometers of it, maybe thousands of kilometers. A diamond mantle wrapped around a metallic core, buried under a thin veneer of lighter elements. No one has directly observed a diamond planet yet. The candidates are hypothetical, based on models of carbon-rich planetary formation. But the chemistry checks out, the physics allows it. And as the exoplanet catalog grows, as we start finding planets around stars with unusual compositions, the odds of detecting a carbon planet increase. Some researchers have proposed that certain super-Earths already discovered might be carbon-rich based on their densities and the properties of their host stars. 55 Cancri E is one candidate that's been discussed in the literature. It's a super-Earth orbiting very close to its star, hot enough that the surface is likely molten, and the host star has a higher carbon-to-oxygen ratio than the Sun. That doesn't prove 55 Cancri E is a diamond planet. It just means it could be. The data isn't conclusive yet, but the possibility sits in the models, waiting for better observations to confirm or rule it out. The idea of a diamond planet captures the imagination because it's exotic. It's the kind of detail that shows up in science fiction. But the real reason it matters is what it says about the diversity of planetary compositions. We built our understanding of planets based on the ones we see in the solar system. Rocky planets are made of silicates. Gas giants are made of hydrogen and helium with traces of heavier elements. Ice giants have water and ammonia and methane. Those are the templates. But if you change the starting conditions, if you change the ratio of elements in the protoplanetary disk, the templates stop working. You get planets made of materials we don't have common names for because they don't exist in large quantities anywhere in our neighborhood. Carbon planets, lava worlds, iron-rich planets with no mantle at all. Each one requires a different formation history, a different set of conditions, and each one tells a different story about what was happening in the disk when the planet formed. The diversity extends to atmospheres. Planetary atmospheres are no longer boring envelopes of nitrogen and oxygen or hydrogen and helium. They're chemically active environments where exotic compounds rain down from the sky. HD 189733b, a hot Jupiter about 64 light-years from Earth, has an atmosphere where silicate particles condense into tiny grains and get whipped around by winds traveling at over 8,000 kilometers per hour. The grains scatter blue light, giving the planet a deep blue color when viewed in visible wavelengths. It looks like Earth from a distance. Same blue hue, but the blue isn't from oceans, it's from silicate dust. Glass. Tiny shards of glass suspended in an atmosphere hot enough to vaporize lead, moving fast enough to sandblast anything in their path. The planet doesn't have weather in the way Earth has weather. It has glass rain driven by supersonic winds. The temperature on the day side exceeds 1,200 degrees Celsius. The night side is cooler, maybe 800 degrees, and that temperature difference drives the wind. Atmosphere flows from the hot side to the cold side and back again in a continuous loop, carrying the glass particles with it. If you were standing on a solid surface in HD 189,733B's atmosphere, which you couldn't because it's a gas giant, the wind would hit you like a blowtorch filled with razors. That's not the only planet with exotic precipitation. WASP-76b, another ultra-hot Jupiter, has temperatures high enough on the day side that iron vaporizes. The iron vapor gets carried to the night side by winds, where it cools and condenses into liquid droplets. Iron rain, not metaphorical. Actual molten iron falling from the sky on the night side, where the temperature is just cool enough for iron to exist as a liquid. The droplets fall toward the interior, heat up again, evaporate, get carried back to the day side by circulation currents, and the cycle repeats. The entire planet is a weather system where metal behaves like water. Kepler-10b, a rocky planet orbiting extremely close to its star, is thought to have seas of lava on its day side, not underground magma chambers, seas. Lakes of molten rock on the surface, fed by the intense heat from the star, possibly driving a weather system where rock evaporates, forms clouds, and rains back down as liquid stone. The idea sounds like bad science fiction, but the temperature and pressure conditions support it. The day side of Kepler-10b reaches over 2,500 degrees Celsius. Basalt melts at around 1,200 degrees. Granite melts closer to 1,000 degrees. At 2,500 degrees, most rocky materials are either molten or vapor. The planet isn't just hot, it's liquefying. These atmospheres, these weather systems, they're not anomalies. They're what happens when you take familiar materials, water, silicates, metals, and subject them to conditions that don't exist anywhere in our solar system. Earth's weather is driven by water. Water vapor rises, cools, condenses into droplets, falls as rain. The same process works on other planets, but the working fluid changes. On Venus, it's sulfuric acid. On Titan, it's methane. On HD 189,733b, it's glass. On WASP-76b, it's iron. The physics is the same, the chemistry is different. And the outcomes are strange enough that when astronomers first detected these signatures in exoplanet atmospheres, some of them didn't believe the data. Glass rain sounded too weird. Iron rain sounded made up. But the spectroscopic evidence kept coming back with the same results, and eventually the field accepted it. These planets exist, these processes are happening. The universe doesn't care if the weather sounds implausible. The James Webb Space Telescope is changing the game here. Webb's infrared instruments can analyze exoplanet atmospheres in detail that was impossible with earlier telescopes. Hubble could detect the presence of certain molecules by looking at how starlight filters through a planet's atmosphere during a transit. Webb can do that and more. It can measure the abundance of specific compounds, map temperature variations across the day side and night side, detect trace gases present in tiny concentrations, distinguish between different chemical processes driving atmospheric dynamics. The data coming back from Webb's first few years of operation has already expanded the catalogue of known atmospheric compositions, and the pace is accelerating. Every few months, a new paper announces the detection of some molecule no one expected to find in that particular planet's atmosphere, and the models scramble to catch up. The trend is clear. The more we look, the stranger the planets get. WASP-17b orbits backward. PSR J1719-1438b is made of diamond. HD 189,733b rains glass. WASP-76b rains iron. Kepler-10b might have lava seas. And these are just the ones we've studied in enough detail to say anything definitive about. The exoplanet catalogue contains thousands of confirmed planets and thousands more candidates waiting for follow-up observations. Most of them haven't been analyzed beyond the basics. Mass, radius, orbital period. We know they exist. We don't know what they're made of or what their atmospheres look like. And if the detailed studies we've done so far are any indication, a significant fraction of those planets are going to turn out to be just as strange as the ones we've already highlighted. The pace of discovery is accelerating. Kepler found about 2,700 confirmed exoplanets during its mission. TESS, the Transiting Exoplanet Survey satellite, is finding more, and it's surveying a much larger fraction of the sky. Ground-based surveys are improving. New detection methods are being developed. Techniques like transit spectroscopy, phase curve analysis, and direct imaging are becoming routine. The James Webb Space Telescope is operational. The Nancy Grace Roman Space Telescope will launch in the mid-2020s with instruments specifically designed to image exoplanets and study rogue planets. The European Space Agency's Plato mission is scheduled for the late 2020s, designed to find rocky planets in habitable zones around sun-like stars and characterize their atmospheres. The field is expanding faster than it ever has, and every new instrument, every new mission pushes the boundaries of what we can detect. And here's the uncomfortable part. The planets we're finding aren't getting more normal. They're getting weirder. The first exoplanets discovered were hot Jupiters because those were the easiest to detect. Big planets, close orbits, strong signals, and even those were strange compared to our solar system. Then we found super-Earths, then mini-Neptunes, then ultra-short period planets, then planets orbiting binary stars, then planets orbiting white dwarfs, then planets in retrograde orbits, then rogue planets. Each wave of discoveries added a new category of planet that didn't exist in the template we built from our solar system. And there's no sign the process is slowing down. If anything, it's speeding up. The concept of a normal planet is dissolving. For most of human history, normal meant Earth. Rocky, temperate, orbiting a sun-like star at a comfortable distance. Then we learnt about the other planets in the solar system, and normal expanded to include gas giants and ice giants. Then exoplanets came along, and normal exploded into a spectrum that includes hot Jupiters, super-Earths, lava worlds, ice giants orbiting close to their stars, gas giants orbiting backward, planets with no stars, and worlds where the atmosphere is made of vaporized metal. Normal doesn't mean anything anymore, or rather, it means something different than it used to. Normal is whatever the universe decides to build, and the universe has more imagination than we do. The question astronomers are starting to ask isn't what kinds of planets are possible. It's what kinds of planets are impossible. And the uncomfortable answer, based on the last 3 decades of exoplanet discovery, is that the list of impossible planets keeps shrinking. Every time someone says a certain configuration can't exist, someone else finds a planet in exactly that configuration. Planets too close to their stars, planets too big for their density, planets orbiting dead stars, planets with no stars, planets made of materials that shouldn't be there. The universe is not respecting the boundaries we drew, it's ignoring them. That trend has implications for how we search for habitable planets. If planets can form in configurations we didn't predict, if they can exist in environments we thought were sterile, if atmospheric chemistry can produce outcomes we didn't expect, then the definitions we're using for habitability might be too narrow. We've been looking for Earth-like planets because Earth is the one example we have of a planet that supports life. But what if life doesn't require an Earth-like planet? What if it can start on a super-Earth with a thick hydrogen atmosphere? What if it can survive on a planet orbiting a red dwarf, where the radiation environment is harsh, but the temperature allows liquid water? What if it can emerge on a moon orbiting a rogue planet, heated by tidal forces, with no star in the sky? The more diverse planets turn out to be, the wider the range of environments we need to consider when we talk about habitability. The James Webb Space Telescope is already looking. One of its primary science goals is to analyze the atmospheres of rocky planets in habitable zones and search for biosignatures, oxygen, methane, combinations of gases that don't make sense unless something is actively producing them. Life, in other words. But Webb is also finding that atmospheres are more complicated than the simple models predicted. More clouds, more hazes, more chemical pathways that produce false positives or mask real signals. The search for life is harder than anyone thought it would be when the mission was designed, not because life doesn't exist, we don't know if it does, but because the backgrounds are messy, atmospheres are noisy, and distinguishing a biosignature from a chemical quirk requires data that's right at the edge of what current instruments can collect. And that brings us to the broader point. Every strange planet we find, every impossible configuration we confirm, every exotic atmosphere we analyze, all of it expands the map of what's possible. And that map is the foundation for every question we ask about where life might be and what it might look like. If planets are more diverse than we thought, life's options are more diverse too. And if we're serious about finding life beyond Earth, we need to stop assuming it will look like Earth and start preparing for the possibility that it will look like something we haven't imagined yet. The next chapter is about method, about how we actually detect these impossible planets from tens or hundreds or thousands of light years away, how we measure their mass, their size, their temperature, their atmospheric composition, how we distinguish between a planet and a brown dwarf, between a hot Jupiter and a stellar remnant, between a real signal and an instrumental artifact. Because all of this, every strange planet we've discussed, every weird orbit and exotic atmosphere, is built on data, observations, measurements. And those measurements are hard, harder than most people realize. The fact that we can do this at all, that we can point a telescope at a distant star and figure out that there's a planet orbiting it, and that the planet is raining glass, or orbiting backward, or drifting alone through space, that's not just astronomy, it's detective work. And the tools we use, the techniques we've developed, are the reason we know any of this in the first place. We left the catalogue of impossible planets stacking up like evidence in a case no one knows how to close. Planets orbiting backward, planets raining iron and glass, worlds covered in lava seas, rogue planets drifting alone through the void. Diamond planets that might exist if the chemistry lines up right. Every category a contradiction, every discovery a reminder that the universe builds things we didn't predict and doesn't ask permission before doing it. The list keeps growing, and the models keep scrambling to catch up. And at some point you have to stop and ask a more fundamental question, not what these planets are or why they exist, but how. How do we know any of this? How can astronomers, sitting on a planet orbiting an ordinary star in an ordinary galaxy, point a telescope at a patch of sky hundreds or thousands of light years away and figure out that there's a planet there, and not just that there's a planet, but that the planet is twice the size of Jupiter, orbits its star every 3 days, has an atmosphere made of vaporized metal, and is raining molten iron on its night side? How is that even possible? What chain of observations and measurements and calculations allows someone to look at a dot of light in a telescope and extract that much information from it? The answer is not simple. It's not one technique. It's a combination of methods, each one designed to tease out a different piece of the puzzle, and each one working at the absolute edge of what current technology can detect. The science of finding exoplanets is a masterclass in indirect observation. We can't see the planets directly most of the time. They're too far away, too faint, too close to their stars. What we see are effects, shadows, wobbles, flickers, tiny distortions in light that tell us something is there even when we can't resolve it as an image. And from those effects, from those hints buried in the noise, we reconstruct entire worlds. Start with the method that's found more planets than any other, transit photometry. The name sounds technical, but the concept is straightforward. Watch a star, measure its brightness. If a planet crosses in front of the star from our perspective, the star dims slightly, not by much. For a Jupiter-sized planet transiting a Sun-like star, the dip is about 1%. For an Earth-sized planet, it's more like 0.01%, 0.01%. That's the signal you're looking for, a tiny periodic dip in a star's brightness that repeats on a regular schedule. Detect that dip, measure how deep it is and how long it lasts, and you can calculate the planet's size and orbital period. That's it. That's the transit method. Conceptually, it's simple. In practice, it's brutally difficult because stars are not perfect light bulbs. They flicker, they have spots. They have magnetic activity that causes their brightness to vary on timescales ranging from minutes to years. And the signal you're trying to detect, the planet's transit, is buried underneath all of that noise. You're looking for 0.01% brightness change in a star that's already varying by 0.1% just because it's a star. It's like trying to hear a whisper in a crowded bar. The whisper is there, you just have to filter out everything else first. NASA's Kepler Space Telescope was built specifically to solve this problem. Launched in March 2009, Kepler was designed to stare at a single patch of sky containing about 150,000 stars and monitor their brightness continuously for years, not occasionally. Not when the weather was good or when someone remembered to point the telescope in the right direction. Continuously, 24 hours a day, no interruptions, no gaps. The only way to detect transits reliably is to watch long enough to catch multiple events. One dip could be a fluke, an instrumental glitch, a sunspot. 2 dips start to look like a pattern. 3 dips and you've got an orbit. The planet comes back like clockwork, and the period between transits tells you how long it takes to go around its star. Kepler's mission was stunningly successful. By the time the telescope's primary mission ended in 2013, when a reaction wheel failed and the spacecraft lost its ability to point precisely, it had identified thousands of planetary candidates, thousands, in one tiny patch of sky, representing about 1/4% of the total celestial sphere. Do the math and extrapolate that out to the whole galaxy, and you get a number so large it stops sounding real. Billions of planets, tens of billions, maybe hundreds of billions. The Milky Way isn't a collection of stars with occasional planets. It's a galaxy where nearly every star has planets, and the planets outnumber the stars by a wide margin. But the transit method has limitations, big ones. For a planet to transit, it has to pass directly between its star and Earth. The alignment has to be perfect. If the planet's orbit is tilted even slightly, if it passes above or below the star from our perspective, we see nothing, no dip, no signal. The planet is invisible to the transit method. Estimates suggest that for a random planetary system, the odds of seeing a transit depend on the planet's orbital distance. For a planet orbiting as close as Mercury, the probability is a few percent. For a planet at Earth's distance, it drops to about 0.5%. For a planet at Jupiter's distance, it's 0.1%. Most planets don't transit. Most systems are tilted the wrong way. What Kepler found, what every transit survey finds, is a biased sample. The planets we detect are the ones whose orbits happen to line up with our line of sight, and that introduces a systematic bias into the data. Transit surveys are excellent at finding large planets close to their stars because those planets block more light and transit more often. A hot Jupiter transiting every 3 days will show up clearly in a few weeks of observations. An Earth analog transiting once per year takes years to confirm because you need multiple transits to be sure the signal is real. That's why the early exoplanet catalogs were dominated by hot Jupiters. Not because hot Jupiters are the most common type of planet, although they are common, but because they're the easiest to find with the transit method. Big planets, short orbits, strong signals. As the surveys got longer and the instruments got more sensitive, smaller planets started showing up. Super-Earths, mini-Neptunes, rocky planets in temperate orbits. But even now, the transit method struggles with planets in wide orbits around faint stars. The signals are too weak, the transits too infrequent. We're still biased toward finding planets that are either large or close, or both. The second major detection method doesn't rely on transits at all. It measures the star's motion, radial velocity, sometimes called Doppler spectroscopy. The idea is that planets don't actually orbit their stars. That's an approximation. What actually happens is that both the planet and the star orbit their common center of mass. For a massive star and a small planet, the center of mass is so close to the star's center that the difference is negligible, but it's not zero. The star wobbles slightly. As the planet orbits, it tugs on the star, pulling it toward the planet, then away, then toward again in a regular cycle. That wobble changes the star's velocity relative to Earth. When the star is moving toward us, the light we receive is blue-shifted, compressed to slightly shorter wavelengths. When it's moving away, the light is red-shifted, stretched to longer wavelengths. The shift is tiny. For a Jupiter mass planet orbiting a Sun-like star at Jupiter's distance, the velocity change is about 12 meters per second. For an Earth mass planet at Earth's distance, it's about 9 centimeters per second. 9 centimeters per second, that's slower than walking. And we can measure it from dozens or hundreds of light years away by analyzing the star's spectrum with enough precision to detect shifts of a fraction of a wavelength. The radial velocity method has its own strengths and weaknesses. It's excellent at finding planets that don't transit because it doesn't require the orbit to be aligned with our line of sight. As long as the planet's orbit has some component of motion toward or away from us, the radial velocity signal is there. It's also good at measuring the planet's mass, or at least a minimum mass, because the amplitude of the wobble depends on how hard the planet is pulling on the star. A massive planet close to its star produces a large wobble. A small planet far from its star produces a tiny wobble. Combine radial velocity with transit data and you get both the planet's size and its mass, and from those two numbers you can calculate density. That's how we know HD 189,733b is a gas giant and Kepler 10b is rocky. Density, mass divided by volume, a number that tells you what the planet is made of without ever having to visit it. But radial velocity has problems too. The biggest one is stellar activity. Stars aren't smooth, featureless spheres. They have spots. They have convection cells. They have magnetic fields that shift and evolve over time. All of that activity introduces noise into the star's spectrum, and that noise can mimic or mask the signal from a planet. A large star spot rotating across the visible hemisphere of a star changes the star's apparent velocity because the spot is cooler than the surrounding photosphere and the light coming from it is redder. That looks like a redshift, a signal that could be mistaken for a planet. Distinguishing real planetary signals from stellar noise requires careful analysis, long observation campaigns, and sometimes a bit of luck. The smaller the planet, the harder the detection. Earth-mass planets around Sun-like stars are right at the edge of what current radial velocity instruments can detect, and most detections in that regime are tentative, possible, not confirmed. The noise floor is too high. And then there's direct imaging, the hardest method, the one that sounds simplest, but is actually the most technically demanding. Point a telescope at a star, block out the star's light with a device called a coronagraph, or a star shade. Look for faint points of light near the star. If you see one that's moving with the star, and not just a background object, that's a planet. You've imaged it directly. You're looking at photons that came from the planet itself, not from the star. That opens up an entirely different kind of science, because now you can study the planet's light. Take a spectrum, measure its temperature, analyze its atmosphere, figure out what it's made of. The problem is the contrast ratio. A star like the Sun is roughly 10 billion times brighter than an Earth-like planet orbiting at 1 astronomical unit. 10 billion. That's the difference between a searchlight and a candle a kilometer away. Blocking out the star's light well enough to see the planet requires instruments that are so precise, so carefully designed, that even tiny imperfections in the telescope's optics or alignment ruin the image. And the planet has to be far enough from the star that you can resolve it as a separate object. Planets close to their stars are lost in the glare, no matter how good your coronagraph is. The ones we can image directly are young, hot, self-luminous gas giants orbiting far from their stars. Planets like 51 Eridani b, HR 8799 b, Beta Pictoris b. Worlds that are still warm from their formation, glowing in the infrared, sitting far enough from their stars that a telescope can separate the two. Direct imaging has its own biases. It finds planets that are big, hot, and far from their stars, the exact opposite of what the transit method finds, and it misses everything else. Small planets, cool planets, planets close to their stars, all invisible. But what it does find, it studies in detail. Spectra taken with direct imaging have revealed clouds, weather, atmospheric circulation patterns, chemical abundances, things you can't get from a transit or a radial velocity signal alone. Direct imaging turns planets from points of light into physical objects with properties you can measure. The real power comes when you combine methods. Find a planet with the transit method. Confirm its mass with radial velocity. If it's bright enough and far enough from its star, image it directly and take a spectrum. Each technique adds a layer of information. Transit data gives you size and orbital period. Radial velocity gives you mass. Spectroscopy gives you atmospheric composition. Put it all together and you have a planet's biography, where it is, what it weighs, what it's made of, how hot it is, whether it has clouds, whether those clouds are made of water or silicates or iron, whether the atmosphere is clear or hazy, whether the planet is losing mass or stable. The tool that's revolutionizing atmospheric characterization is spectroscopy. When light from a star passes through a planet's atmosphere during a transit, some wavelengths get absorbed by molecules in the atmosphere and some pass through. The result is a transmission spectrum, a graph showing how much light made it through at each wavelength. Molecules have fingerprints. Water vapor absorbs strongly at certain infrared wavelengths. Carbon dioxide has its own signature, methane, sodium, potassium. Each one leaves a distinct pattern in the spectrum, and by analyzing that pattern, you can figure out which molecules are present and in what concentrations. It's chemistry from a distance. The same principle works for emission spectra, where you measure the light coming directly from the planet's atmosphere, usually when the planet passes behind the star, and you can isolate the planet's thermal emission from the star's light. This is how we know WASP-76b rains iron. Spectroscopy detected neutral iron in the planet's night-side atmosphere and ionized iron on the day side, and the only explanation that fits the data is that iron vapor on the hot side condenses into liquid droplets on the cooler side and falls as rain. It's not a guess. It's a conclusion drawn from multiple spectra taken over multiple transits, analyzed with atmospheric models that predict how iron behaves at those temperatures and pressures. The same technique identified titanium oxide in the atmospheres of the hottest gas giants, silicate clouds in others, and water vapor in dozens. Spectroscopy has turned exoplanet atmospheres from theoretical constructs into measurable environments. And the James Webb Space Telescope is pushing spectroscopy into a new regime. Webb's infrared instruments are so sensitive that they can detect molecules present in trace amounts, parts per million or parts per billion, in the atmospheres of planets hundreds of light years away. Webb can distinguish between different isotopes of the same element, which tells you about the planet's formation history and whether its atmosphere has been processed by chemical reactions over time. Webb can measure temperature profiles, mapping how temperature changes with altitude in the atmosphere, which tells you about energy transport and weather. The data Webb is collecting isn't just better than what came before, it's qualitatively different, more detailed, more precise, more informative. Every method has its biases, every telescope has its limitations. The planets we've found are the ones our tools can detect, not a representative sample of what's actually out there. Hot Jupiters are overrepresented because they're easy to find with transits and radial velocity. Young giant planets far from their stars are overrepresented in direct imaging surveys because those are the only ones bright enough to image. Small rocky planets in temperate orbits are underrepresented everywhere because they're hard to detect with any method. That skew, that observational bias, is why the early exoplanet catalogues looked so strange. The universe wasn't building an unusual number of hot Jupiters. We were just better at finding them. As the surveys improve, as the instruments get more sensitive, the catalogue is filling in. Smaller planets, cooler planets, planets in wider orbits. The bias is shrinking, but it hasn't gone away. We still can't detect an exact Earth analog around a Sun-like star with current technology. The signal is too weak, the transit too shallow, the radial velocity wobble too small. We're close. The next generation of telescopes, instruments like the Extremely Large Telescope and the 30-meter telescope, both under construction, will get us there. But right now, the planets we study are the ones that shout loud enough for us to hear them. The quiet ones, the Earths and super-Earths in temperate orbits around ordinary stars, most of them are still invisible. And yet, even with these biases, even with the limitations, the diversity we've uncovered is staggering. Thousands of confirmed planets, dozens of them studied in enough detail to characterize their atmospheres, categories of planets that don't exist in our solar system. Hot Neptunes, super-Earths, mini-Neptunes, ultra-short period planets, planets orbiting backward, planets with no stars. Every new detection expands the catalogue. Every detailed study adds nuance. The universe is more creative than we gave it credit for, and the tools we've built to study it are finally good enough to start appreciating that creativity. The ingenuity required to pull this off is easy to underestimate. Measuring a star's brightness to a precision of 1 part in 10,000 over months or years, detecting velocity shifts of meters per second or centimeters per second in objects hundreds of light years away, blocking out a star's light well enough to photograph a planet 1 billion times fainter sitting right next to it. These are not easy problems. They're engineering challenges that took decades to solve, and in some cases, they're still only partially solved. The fact that we can do any of this is a testament to the cleverness of the people designing the instruments and analyzing the data. Take the transit method. Kepler's detector was a 95-megapixel camera, one of the largest ever flown in space at the time. It had to be that large to monitor 150,000 stars simultaneously, and it had to be stable, extraordinarily stable. Any drift in the telescope's pointing, any thermal expansion in the structure, any vibration from the reaction wheels, all of it introduced noise that could swamp the tiny transit signals. The spacecraft was designed to point at the same patch of sky for years without moving. No slewing to new targets, no reorienting for communications, just staring. And it worked. For 4 years, Kepler stared, and the data poured in, and the planet count climbed into the thousands. The radial velocity method has its own technical demands. To measure velocity shifts of centimeters per second, you need a spectrograph stable enough that its own internal mechanics don't shift by more than that over the course of months. Temperature changes, mechanical stress, gravitational sag as the telescope moves across the sky. All of it has to be controlled or calibrated out. Modern radial velocity instruments are marvels of precision engineering. Some are housed in vacuum chambers to eliminate thermal fluctuations. Some use laser frequency combs, devices borrowed from atomic physics labs, to calibrate the spectrograph's wavelength scale to within a billionth of a meter. The effort required to detect a single Earth-mass planet around a sun-like star is immense, and most attempts fail because the star's noise swamps the signal. Direct imaging requires adaptive optics, systems that measure distortions in Earth's atmosphere caused by turbulence and correct for them in real time by deforming a mirror hundreds or thousands of times per second. Without adaptive optics, ground-based telescopes can't achieve the resolution needed to separate a planet from its star. Even with adaptive optics, the images are barely good enough. Space telescopes avoid the atmosphere entirely, but they have their own challenges: diffraction, scattered light, thermal stability. Webb's coronagraphs are engineering masterpieces designed to suppress starlight by factors of 10,000 or more, but even they have limits. And the data analysis, the process of turning raw observations into confirmed planets, is as much art as science. Algorithms sift through light curves, looking for periodic dips that match the expected shape of a transit. Statistical tests rule out false positives. Follow-up observations with different instruments confirm or reject candidates. It's a pipeline, and every step has to work correctly or the final result is garbage. The false positive rate in early exoplanet catalogs was high enough that some detections were later retracted when better data showed the signal was an artifact. The field learned from those mistakes. Modern catalogs are more conservative. Detections require higher confidence levels. Follow-up is mandatory, but the process is still imperfect. Some planets in the catalogs are real, some are probably real, some are questionable. The uncertainties are baked into the numbers. The ground-based observatories play a critical role because they can provide long-term monitoring and high-resolution spectroscopy that space telescopes can't match. Facilities like the European Southern Observatory's Very Large Telescope, the Keck Observatory in Hawaii, and the Gemini telescopes have contributed radial velocity measurements, direct imaging, and spectroscopic follow-up for hundreds of planets. They're the workhorses of the field, operating night after night, collecting data, refining orbits, measuring masses. Space telescopes get the headlines because they produce the dramatic images and the big discoveries, but the ground-based observatories do the heavy lifting. And the space telescopes, for all their precision, are expensive and limited. Kepler cost $600 million and observed one patch of sky. Webb cost $10 billion and is shared among dozens of science programs. Observing time is competitive, oversubscribed by factors of 10 or more. Every exoplanet observation competes with observations of distant galaxies, star-forming regions, black holes, and everything else astronomers want to study. The planets we know the most about are the ones that got prioritized, the ones interesting enough or accessible enough to justify the telescope time. That introduces another bias. The weird planets get studied because they're weird. The boring planets, the ones that are just slightly larger than Earth and orbit slightly closer than Mercury, those often get skipped because there are too many of them and not enough time. The result is a catalogue that's simultaneously vast and incomplete. Thousands of planets, dozens characterized in detail, millions more waiting to be discovered. The number of stars in the Milky Way that have been surveyed for planets is still a tiny fraction of the total. Kepler looked at 150,000. TESS is surveying about 200,000. There are hundreds of billions of stars in the galaxy. We've barely started, and every survey that goes deeper, every instrument that gets more sensitive, finds more planets. The catalogue isn't leveling off, it's accelerating. The methods we use, the techniques that allow us to find planets and characterize them, are the reason we know any of this. Without transits, we'd never have found thousands of planets. Without radial velocity, we wouldn't know their masses. Without spectroscopy, their atmospheres would be blank slates. The science of the impossible isn't about the planets being impossible. It's about the observations being so difficult, so precise, so technically demanding that the fact we can do them at all feels impossible, and yet we do. Every night, every observation, every new data set, the tools get better, the catalogues get longer, the planets get stranger, and the strangest part is that we're still in the early phase of this. The first confirmed exoplanet around a sun-like star was announced in 1995. 29 years ago, less than 3 decades. In that time, we've gone from knowing 8 planets, the ones in our solar system, to knowing thousands, from thinking planets were rare to knowing they're common, from assuming planetary systems look like ours to realizing ours is unusual. The pace of discovery is so fast that textbooks are outdated by the time they're published. The models that explain planet formation are being rewritten constantly. The definitions of what counts as a planet, what counts as habitable, what counts as worth studying, all of it is in flux. And that brings us to the final question, the one that sits underneath all of this. What do these planets mean? What does it tell us about the universe that it builds worlds like this? Worlds that shouldn't exist, worlds that defy our models, worlds so strange that the first time someone proposes them, half the field doesn't believe the data. What does it mean that the galaxy is full of hot Jupiters and rogue planets and worlds where it rains glass? What are we supposed to take away from the fact that every prediction we made based on our solar system turned out to be wrong, or at least incomplete, and the universe is far more diverse than we imagined? That's not a question about technique or observation. That's a question about what it all adds up to, and that's where we're going next. We left the catalogue of impossible planets stacked on a foundation of ingenuity and precision engineering. Telescopes staring at single patches of sky for years. Spectrographs measuring velocity shifts smaller than a human walking pace from hundreds of light years away. Instruments blocking out the light of stars to photograph planets a billion times fainter sitting right next to them. Every detection method pushing against the limits of what physics and technology allow. Every confirmed planet the result of observations so difficult, so demanding, that the fact we can do them at all feels like a minor miracle. And the result of all that effort, all those telescope hours and engineering breakthroughs and careful data analysis, is a catalogue that refuses to make sense. Planets orbiting backward, planets darker than coal, planets where the ice burns at 800 degrees Fahrenheit. Worlds covered in lava seas, atmospheres raining glass and iron, gas giants so bloated they'd float in water, rocky planets orbiting so close to their stars that a year lasts less than a day, rogue planets drifting alone through the void with no star to anchor them, and somewhere out past Neptune, possibly a ninth planet in our own solar system that we've never seen but whose gravitational fingerprints show up in the orbits of distant icy bodies. That last one is worth pausing on because it highlights how much we still don't know about our own neighborhood. In January 2016, Konstantin Batygin and Mike Brown at Caltech announced evidence for a planet roughly 1.5 times Earth's size lurking in the outer solar system. Not based on a photograph, not based on reflected light, based on math. The orbits of certain Kuiper belt objects cluster in ways that don't make sense unless something massive is out there pulling on them. The calculations pointed to a planet 5 to 10 times Earth's mass orbiting the Sun at a distance 20 times farther than Neptune. If it exists, and that's still a big if, it would take 10 to 20,000 years to complete a single orbit. We've been looking for it with telescopes ever since, and we haven't found it. NASA's official position is clear. Planet 9 has not yet been discovered. There is debate in the scientific community about whether it exists. The evidence is suggestive, not conclusive. And the fact that we're even having this conversation, that a major planet in our own solar system could still be hiding from us after centuries of astronomical observation, tells you something important about how much we don't know. The solar system was supposed to be the easy part. We live here. We've sent probes to every major planet. We've mapped the orbits of thousands of asteroids. We've studied comets. We've landed on moons. And yet there might be an entire planet sitting in the outer reaches that we've never seen. If we can miss a planet in our own backyard, what are we missing everywhere else? The exoplanet catalogue has forced a reckoning with that question. Every strange planet we've found, every impossible configuration we've confirmed, expands the boundaries of what we thought was possible. And the expansion isn't slowing down, it's accelerating. The more we look, the stranger things get. TRIAS 2b, the darkest known exoplanet, reflects less than 1% of the light that hits it. Darker than charcoal, darker than coal. A gas giant orbiting its star so close that its year lasts less than a day and a half, and its surface temperature reaches over 4,000 degrees Celsius. Hot enough that the faint red glow from its own thermal radiation is the only reason you'd see it at all if you looked at it up close. The planet swallows light, absorbs it into an atmosphere filled with titanium oxide and vanadium oxide and sodium and potassium, compounds that soak up visible light across almost the entire spectrum. The models predicted that hot Jupiters would be darker than Jupiter because the heat prevents reflective clouds from forming. But the models didn't predict a planet this dark. TRIAS 2b sits at the edge of what atmospheric chemistry allows, and no one is entirely sure why it's quite this extreme. At the opposite end of the spectrum, literally, there's a planet so reflective it acts like a mirror. About 73% of incoming light bounces straight back into space. The planet completes an orbit in less than 24 hours, racing around its star so fast that a single year is shorter than a single day on Earth. The reflectivity comes from clouds, metallic clouds. The upper atmosphere is filled with particles of silicate and possibly metal oxides that scatter light with brutal efficiency. The planet is bright, painfully bright. If TRIAS 2b is a hole in space, this one is a searchlight. The gap between those two extremes tells you everything you need to know about how diverse planets can be. Same basic category, gas giants orbiting close to their stars, similar temperatures, similar sizes, completely opposite appearances. One swallows light, the other throws it back. And both are real, both exist. Both are out there right now, orbiting their stars, doing what they do, indifferent to whether we understand them or not. And then there are the ones that shouldn't survive. GJ 436b, an evaporating hot Neptune, orbits its star in less than 1.1 days. The radiation from the star is stripping away the planet's atmosphere layer by layer, blowing hydrogen into space in a constant stream that forms a comet-like tail stretching for millions of kilometers behind the planet as it orbits. The planet is dying, not quickly. The process will take millions of years, but it's measurable. We can watch it happen in real time, or at least in astronomical real time, which means watching the same system over years and seeing the changes add up. GJ 436b is spiraling inward. The tidal forces are pulling it closer to its star with every orbit, and eventually, maybe in a few 100 million years, maybe in a billion, the planet will cross the Roche limit and be torn apart. What's left will be scattered into the stellar wind or swallowed by the star. Either way, the planet won't survive. It's temporary, a geological accident waiting to be undone. Kepler 78b is in the same category. About 1.2 times Earth's radius, 1.7 times Earth's mass, orbiting about 100 times closer to its star than Earth orbits the Sun. The surface temperature is over 2,000 degrees Celsius. The planet is tidally locked, meaning the same side always faces the star. The day side is a sea of molten rock. The night side is only slightly cooler, maybe 1,500 degrees, because the winds racing around the planet redistribute some of the heat. A year lasts 8.5 hours. The planet completes 4,200 orbits in the time it takes Earth to go around the Sun once. And like GJ 436b, Kepler 78b is doomed. The orbit is decaying. Tidal interactions with the star are stealing energy from the planet's orbital motion and converting it into heat. The planet is being cooked from the outside by stellar radiation and from the inside by tidal friction. Eventually, it will spiral into the star and vaporize. The timeline is uncertain. Could be 10 million years, could be 100 million. Either way, Kepler 78b is living on borrowed time, and we're watching it die. The existence of planets like these, planets in configurations that guarantee their destruction, raises an uncomfortable question. How many planets has the universe built and then destroyed? How many worlds formed in stable orbits, migrated inward, got caught in death spirals with their stars, and evaporated before anyone could observe them? The planets we see, the ones in the catalogue, are survivors, or at least they're surviving for now. But the catalogue only includes the ones that are still here, the ones that got destroyed millions or billions of years ago, before humans built telescopes, before Earth had multicellular life, before the solar system even formed. Those planets are gone, erased. The only evidence they ever existed is maybe a slight overabundance of heavy elements in their host star's spectrum, a chemical signature showing that the star swallowed something, and even that fades over time as the star's convection mixes the material into the interior. The universe is full of dead planets, planets that used to exist and don't anymore, and we'll never know how many there were because the evidence is gone. What we see in the exoplanet catalogue is a snapshot, a single frame from a movie that's been running for billions of years. The hot Jupiters we observe today might not be here a billion years from now. Some will spiral into their stars. Some will have their atmospheres stripped away until nothing's left but a dense core. Some will get ejected by gravitational interactions with other planets and become rogues. The catalogue is constantly changing, and we're only now developing the tools to measure those changes. And the strangest planets, the ones that defy explanation, are the ones that teach us the most, because outliers don't just break the models, They force you to rebuild them. The model that explains only the typical cases is a model that's incomplete. A model that explains the extremes, the edge cases, the planets that shouldn't exist, that's a model that might actually be capturing something fundamental about how the universe works. Take hot Jupiters. When the first one was discovered in 1995, 51 Pegasi b, the reaction in the field was skepticism. Gas giants don't orbit that close to their stars. The physics doesn't allow it. There's not enough solid material in the inner disk to build a core massive enough to capture hydrogen and helium. The planet has to form farther out, beyond the frost line, where it's cold enough for ice to condense. That's the rule. That's how Jupiter formed. And 51 Pegasi b was violating the rule. Some astronomers assumed the detection was wrong, an artifact, a mistake in the data. It took follow-up observations, additional detections, and years of debate before the field accepted that hot Jupiters are real. And once that happened, once the denial phase ended, the models had to change. Planetary migration was added to the story. Planets can move. They can spiral inward through interactions with the protoplanetary disk or through gravitational scattering with other planets. The orderly picture of planetary formation, where everything forms in place and stays there, collapsed, replaced by something messier, more dynamic, more violent, a picture where planets get thrown around, where orbits change, where some planets survive and others get ejected or destroyed. That revision happened because the universe built something that didn't fit the model. And the universe keeps doing it. Every new category of planet, every configuration that shouldn't work, forces another round of model updates. Super-Earths exist, and we don't know why our solar system doesn't have one. Planets orbit backward, and we don't fully understand what sequence of events produces a retrograde orbit. Planets with no stars drift through the void, and we're still counting how many there are. Rogue planets might outnumber stars in the galaxy. That's not a fringe theory anymore. That's a possibility supported by simulations and detections and statistical extrapolations. If it's true, if there are more rogue planets than stars, the galaxy is a fundamentally different place than we thought. Not a collection of solar systems, a sea of darkness with islands of light, and between the islands, billions of worlds moving alone. The philosophical weight of that is hard to overstate. We think of planets as places, locations, objects orbiting stars, anchored by gravity, part of systems. But if most planets don't orbit anything, if most are drifting, then a planet isn't a place, it's just an object. A ball of matter moving through space with no destination, no future except the slow march toward thermal equilibrium with the background radiation of the universe, absolute cold, perfect stillness, and eventually heat death. The same fate awaiting everything else, but without even the temporary warmth of a star to delay it. That fate is billions of years away for most rogue planets. The ones we've detected are young, still glowing with the heat of their formation. PSOJ 318.522, the free-floating gas giant discovered in 2013, is only about 12 million years old. It's still warm, surface temperature around 1100 degrees Celsius, emitting a faint red glow that our infrared telescopes can pick up from 80 light-years away. But the glow is fading. The planet is cooling. Every joule of thermal energy it radiates into space is gone forever. There's no star to replenish it, no tidal heating from a nearby companion. Just the planet and the void is patient. In another 100 million years, PSOJ 318.522 will be too cool to detect with current instruments. It will still exist, still moving, still out there, but invisible, a ghost, and it will keep cooling, and in a few billion years it will be indistinguishable from the cold darkness around it, a world that exists but cannot be seen. The loneliness of a rogue planet is absolute. No sunrise, no seasons, no moon unless it brought one with it when it was ejected. Nothing changes. The stars in the sky, from the planet's perspective, shift position over thousands of years as the planet drifts, but the sky itself is always black, always empty, no star bright enough to cast a shadow. Just the faint scattered light of distant suns, too far away to matter. If life somehow started on a rogue planet, maybe on a moon heated by tidal forces, it would never know what a star was. It would have no concept of day or night, no reason to look up because there's nothing up there to see. A biosphere in permanent isolation, cut off from the rest of the universe by distance and darkness. It's possible, maybe even plausible if the conditions are right, but undetectable. We'd never find it unless we stumbled onto it by accident, and the odds of that are vanishingly small. The existence of rogue planets forces a revision to how we think about habitability. For decades, the habitable zone was defined as the region around a star where liquid water can exist on a planet's surface. Too close and the water boils. Too far and it freezes. The habitable zone is the Goldilocks strip where temperatures are just right. Earth sits comfortably in the middle of the sun's habitable zone, and that's one of the reasons life had a chance to develop here. The search for habitable exoplanets has focused almost entirely on finding rocky planets in the habitable zones of other stars. Find a planet the right size, at the right distance from a sun-like star, and you've found a candidate for life. That's the logic, and it's good logic as far as it goes. But rogue planets break that framework. They don't orbit stars. They're not in habitable zones. And yet some of them might still have liquid water. Deep beneath icy crusts, heated by the decay of radioactive elements in their cores, or heated by tidal forces if they have moons. The energy doesn't come from a star, it comes from within. And if that's enough to maintain liquid water, if it's enough to drive chemistry and provide a stable environment over billions of years, then life doesn't need a sun. It just needs energy and time and the right ingredients. And a rogue planet drifting through interstellar space could have all three. That possibility, remote as it is, widens the scope of where we should be looking for life. Not just planets in habitable zones, not just moons of gas giants in stable solar systems. Anywhere there's liquid water and energy. And if rogue planets outnumber stars, if they're everywhere, drifting through the galaxy unseen, then the number of potential habitats goes up by orders of magnitude. Most of them will be sterile, frozen, dead, but not all. And the ones that aren't, the ones where conditions lined up just right, are out there right now, living, evolving, completely unaware that the rest of the universe exists because they're cut off from it by the vast empty distances between stars. The diversity of exoplanets, the sheer range of environments and configurations, also forces a reckoning with anthropocentrism. For most of human history, we assumed Earth was the center of everything. The universe was built for us. The stars revolved around us. Then Copernicus moved the center to the sun. Then Hubble showed us the universe is expanding and there is no center. Then exoplanets showed us that Earth is one planet among billions, and most of those billions look nothing like Earth. Rocky planets orbiting so close to their stars that the surface is molten. Gas giants puffed up to twice Jupiter's size, with densities so low they'd float. Worlds where the atmosphere is hydrogen or methane or vaporized rock. Planets so hot that molecules break apart. Planets so dark they swallow light. Planets with no stars. Every discovery chips away at the idea that Earth is special. And yet Earth is special in at least one way. It's the only planet we know of that hosts life. That could mean life is rare. So rare that out of billions of planets, only one in our neighborhood has it. Or it could mean we haven't looked hard enough yet, haven't developed the tools sensitive enough to detect biosignatures in the atmospheres of distant worlds. The James Webb Space Telescope is trying. Webb can analyze the atmospheres of rocky planets in habitable zones and search for chemical combinations that don't make sense unless something is actively producing them. Oxygen and methane together, for example, both are reactive. They shouldn't coexist in an atmosphere for long unless something keeps replenishing them. On Earth, that something is life. Photosynthesis produces oxygen. Bacteria and other organisms produce methane. If Webb finds the same combination on an exoplanet, the simplest explanation is biology. But Webb hasn't found it yet. And the more atmospheres Webb studies, the more complicated the picture gets. Clouds obscure signals, hazes scatter light. Chemistry produces false positives or masks real signals. The search for life is harder than anyone expected when the mission was designed. Not because life doesn't exist. We don't know if it does. But because the backgrounds are messy and distinguishing a biosignature from a chemical quirk requires data at the edge of what current instruments can collect. And even if Webb does find something, even if it detects a combination of gases that screams biology, the confirmation process will take years, decades maybe, multiple observations with multiple instruments, ruling out every possible non-biological explanation. The standards for claiming a detection of life are rightly high because the claim is so extraordinary. And in the meantime, the catalogue of lifeless planets keeps growing, thousands of them. Each one a world with its own history, its own chemistry, its own story. None of them hosting life as far as we can tell, all of them expanding the boundaries of what planets can be. The terror and wonder of these alien worlds sit on opposite sides of the same coin. Wonder because the universe is more creative than we imagined. Because planets can be things we never predicted. Because every strange configuration we find tells us the rules are wider than we thought. Terror, because those same planets remind us how hostile the universe is, how fragile Earth's stability is. How lucky we are that our planet formed where it did, when it did, in a system that didn't eject it or fry it or tear it apart. Kepler 78b is being cooked alive, spiraling into its star. GJ 436b is evaporating, losing its atmosphere atom by atom. CRESS 2b is so dark it would look like a hole if you saw it up close. WASP 76b rains molten iron. KELT 9b is hot enough that molecules don't survive. Its atmosphere is individual atoms, stripped of their bonds, glowing with heat. The dayside temperature exceeds 4,000 degrees Celsius, hot enough to vaporize titanium. Iron evaporates. The planet is brighter than some stars, and it's being torn apart by its own proximity to the star it orbits. These are not places, they're warnings, reminders that the universe doesn't build planets for comfort. It builds them because the physics allows it, and sometimes the physics produces nightmares. And yet those nightmares are real, they exist. They're not hypothetical, not theoretical, they're out there, orbiting real stars, measurable, observable, as real as Earth. And the fact that we can study them, that we can point telescopes at them and figure out what they're made of and how hot they are and whether they're losing mass or stable, that's one of the most remarkable achievements of modern science. We've gone from knowing 8 planets to knowing thousands, from assuming planets are rare to knowing they're common, from thinking planetary systems look like ours to realizing ours is unusual. The pace of change is so fast that the textbooks can't keep up. Every edition is outdated by the time it's published because the field keeps finding things that don't fit the old models. The standard model of planet formation, the one built from studying our solar system, assumed planets form in place and stay there. Rocky planets close, gas giants far. Orderly, predictable, stable. That model worked until we looked at other systems and found chaos. Planets migrating inward, planets getting ejected, planets ending up in configurations that shouldn't be stable but are. Retrograde orbits, ultra-short periods, evaporating atmospheres. The model didn't predict any of it. And every time the model fails to predict something, it gets revised. Migration added, scattering added, atmospheric escape added, tidal interactions added. Each revision makes the model more complicated, more flexible, better at explaining the data, but also less predictive. Because the more variables you add, the harder it is to say what should happen in any given system. The model becomes a tool for explaining what we see, not for predicting what we'll find next. And that might be the most important lesson these impossible planets teach us. The universe is not required to follow our scripts. We can write models based on the data we have, and those models will work until they don't, until we find something that breaks them, and then we revise, and the process repeats. Science is not a ladder you climb until you reach the top. It's a map you keep redrawing every time you explore a new region and realize the coastline doesn't match the chart. The map gets better, more detailed, more accurate, but it's never finished. There's always another coastline, another planet, another discovery waiting to force another revision. The planets that shouldn't exist are teaching us humility, teaching us that our assumptions, no matter how well-founded, are always incomplete. That the universe is under no obligation to match our expectations. That the rules we think are universal might just be local. That the sample size we built our models from, 8 planets in one system, was far too small to draw confident conclusions about how planets work everywhere. We assumed Earth was typical. It's not. We assumed gas giants formed far from their stars. They don't always. We assumed planets need stars. They don't. Every assumption we made based on limited data turned out to be a special case, not a universal law. And the humbling continues. Every year, every new detection, every atmosphere analyzed, every orbit measured, the catalog grows, the models adjust, the boundaries expand. And somewhere out there, orbiting a star we haven't surveyed yet, or drifting alone through interstellar space, is a planet stranger than anything we've found so far. A planet that will break the current models the way hot Jupiters broke the old ones. A planet that will force another round of revisions, another rewrite of the textbooks, another acknowledgement that we didn't know as much as we thought we did. That's the story these planets tell. Not a story about Earth being unique or special, not a story about the universe being built for us. A story about a cosmos so vast, so old, so indifferent to what we expect, that it builds billions of worlds, and most of them look nothing like home. Some are too hot, some are too cold, some have no star, some orbit backward, some are so dark they swallow light, some are so bright they blind you, and all of them exist. All of them are real. All of them are out there right now, doing what they do, following the same laws of physics that govern Earth, but producing outcomes so strange that we struggle to find words for them. The terror is that we're not special. The wonder is that we exist at all. Somewhere in the vast catalogue of impossible planets, Earth sits as an outlier in a different direction, not because it's hot or dark or fast or lonely, because it's stable, temperate, old, patient. A planet that formed in the right place at the right time and stayed there long enough for oceans to form and chemistry to get complicated and life to start. That combination is rare, maybe very rare. And the more extreme planets we find, the clearer it becomes that the conditions that allowed life to start here are not the default, they're the exception. And exceptions don't last forever. Earth's habitability is temporary. The sun is getting brighter. In 1 billion years, maybe less, the oceans will boil. In 5 billion years, the sun will expand into a red giant and swallow the inner planets. Earth will either be consumed or scorched into a lifeless cinder orbiting a dying star. The stability we take for granted, the temperate climate and liquid water and protective atmosphere, all of it is a phase, a moment in geological time. And when that moment ends, Earth will join the catalogue of impossible planets as just another dead world orbiting a star that used to be like the sun. The universe will keep building planets, most of them hostile, some of them strange, a few of them maybe stable enough for life. And the process will continue for trillions of years, long after the sun dies, long after every star currently burning has exhausted its fuel, until the universe itself runs out of gas and the lights go out for good. The planets we've found, the ones that shouldn't exist, are a preview of that future, a reminder that planets are temporary, that systems are dynamic, that nothing lasts. The universe is not a museum, it's a construction site, always building, always tearing down, always moving forward into configurations we can't predict and wouldn't believe until we see them. And we're seeing them now, thousands of them, with more coming every year. The impossible planets are teaching us that the universe is stranger than we thought, more diverse, more hostile, more creative. And the only honest response to that knowledge is a mixture of awe and fear. Awe because the scale and variety are overwhelming. Fear because the universe doesn't care. It builds what it builds, destroys what it destroys. And we're watching from one small stable planet that got lucky, knowing that the luck won't last forever, and wondering what else is out there that we haven't found yet. What other impossible things the universe is hiding? What other planets are orbiting distant stars or drifting through the void, waiting for someone to point a telescope in the right direction and realize they exist? That's what these planets teach us. The universe is not ours. We're not the center. We're not the template. We're one outcome among billions, and most of the others look nothing like us. And the fact that we can study those others, that we can catalog them and analyze them and try to understand them, is the only thing that makes the terror bearable. Because if the universe is strange and hostile and indifferent, at least we can look at it, measure it, try to figure out how it works, and maybe, in the process, understand a little better how lucky we are to be here at all. We started this journey asking why 12 planets exist that shouldn't. We catalogued the extremes, the planets burning at temperatures hotter than some stars, the worlds so dark they swallow light and refuse to give it back, the ice that stays frozen at 800 degrees because pressure won't let it melt, the rogue planets drifting alone through the void with no sun, no orbit, no destination except the slow fade into darkness, the gas giants orbiting backward, the atmospheres raining glass and molten iron, the lava seas, the evaporating worlds spiraling toward their stars, losing mass with every orbit, dying in slow motion while we watch. But the real question was never why these planets exist. It was what they mean, and the answer, uncomfortable as it is that they mean Earth is not the template. The solar system is not the blueprint. The rules we wrote based on 8 planets orbiting one star were never universal laws. They were local observations mistaken for cosmic truths. The universe didn't read our textbooks. It built what the physics allowed, and the physics allows almost everything. Worlds in configurations we thought were impossible, atmospheres made of compounds that shouldn't be there, orbits that defy the models, planets with no stars, stars with no planets. And somewhere between the extremes, one temperate world where the conditions lined up just right, just long enough for life to start. We are not the rule, we are the exception, and exceptions are rare. The impossible planets teach us humility. They teach us that the universe is stranger, more diverse, more indifferent than we imagined. That stability is not guaranteed, that the conditions we take for granted are temporary, that most worlds look nothing like home, and that the cosmos has been building and destroying planets for billions of years, long before we were here to notice, and will continue long after we're gone. The universe is not ours, we're just watching. And what we're watching is a story with no author, no plan, no script. Just physics playing out across trillions of years, building worlds because it can, destroying them because it must, indifferent to whether any of it makes sense to the brief sparks of consciousness trying to catalogue it all before the lights go out. As new telescopes listen ever more closely, let these alien worlds sharpen our curiosity, deepen our humility, and deepen our care for the living world beneath us.